Have you ever stood outside on a clear, dark night, looked up at the stars, and felt a sudden, profound sense of your own smallness? That vast, silent, infinite blackness stretching out forever can make our daily worries seem trivial. Our entire lives feel like a fleeting spark in an unimaginable expanse. That feeling, that humbling awe, is just a tiny glimpse into the reality of the cosmos we inhabit. It's a reality filled with wonders, but also with genuine, spine-chilling truths that defy our everyday understanding. Today, we're going to journey beyond that tranquil, starry sky and into the heart of that darkness, to explore 30 facts about space that are not just amazing, but will truly terrify you. We're about to confront the universe's deepest, most unsettling secrets that challenge our very place in the grand scheme of things. From the silent, invisible monsters lurking in the void to the ultimate fate that awaits everything we know, this is not a journey for the faint of heart. This is an exploration of the cosmic phenomena that scientists are only just beginning to comprehend. Phenomena that reveal a universe far stranger and more hostile than we could have ever imagined from our tiny, fragile world. So prepare yourself to have everything you thought you knew about reality turned upside down. We begin with a sound not from our world, but from the depths of interstellar space. It's a rhythmic, metronomic pulse, a beacon from a long-dead star. This is the sound of a pulsar, a rapidly spinning neutron star, and its steady, almost mechanical beat is a haunting reminder that the universe operates on a scale and with forces that are utterly indifferent to our existence. This single, eerie signal is our first step into the unknown, a hint at the chilling truths waiting for us in the darkness. And that haunting cosmic rhythm leads us directly to our first terrifying truth, a danger that is both silent and absolute. The vacuum of space is not simply an empty void. It is an actively hostile environment, a near-perfect vacuum that defies every condition our bodies need to survive. We often see dramatic movie scenes where people explode in the vacuum, but the reality is somehow more insidious and gruesome. You wouldn't pop. Instead, the absence of atmospheric pressure would cause the fluids on the surface of your body to instantly begin to boil. Your saliva would bubble and vaporize on your tongue. The moisture in your eyes would start to fizz. Without the external pressure to keep your blood dissolved with gases, the nitrogen in your bloodstream would come out of solution, fizzing like a freshly opened soda bottle, causing a condition known as ebullism. All of this would happen while you are still horrifyingly conscious. The air in your lungs would be violently ripped out, and because you cannot scream in a vacuum, your final moments would be utterly silent. Your body would swell to nearly twice its normal size, but your skin is tough enough to contain the pressure. So you become a distorted, bloated version of yourself. Consciousness would last for only about 15 seconds as the oxygen left in your blood is depleted. After that, your body, now a frozen, desiccated relic, would continue its momentum, potentially drifting for millions of years through the endless, frigid blackness. There would be no decomposition, no natural end. You would simply be a permanent monument to the universe's profound indifference, a frozen statue on an eternal journey through the stars. This isn't just a sci-fi horror scenario. It's the fundamental, brutal physics of the environment that makes up over 99% of our known universe. An environment that is, in every conceivable way, trying to kill you. But that silent, airless death is not the only invisible killer waiting in the void. If the vacuum is the universe's crushing grip, then cosmic radiation is its silent, poisonous breath. Pouring through space at nearly the speed of light are unimaginably high-energy particles, atomic fragments blasted across the galaxy by the most violent events in existence, supernova explosions and the voracious jets of supermassive black holes. These particles, primarily protons and atomic nuclei, carry so much energy that a single one can possess the force of a Major League Baseball pitch. Here on Earth, we are blissfully shielded from this constant, deadly rain by our planet's magnetic field and thick atmosphere, which act as a protective cocoon. But venture beyond this fragile bubble, and you are exposed to a subatomic hailstorm that never ceases. These particles are so energetic and small that they don't just stop at the surface. They pass directly through the hull of a spacecraft, through your spacesuit, and straight through your body. As they travel, they can smash directly into the delicate strands of your DNA, shattering the molecules and causing irreparable damage to the very blueprint of your cells. This damage can lead to mutated cells that may one day turn cancerous, and it poses a catastrophic risk to the central nervous system, potentially accelerating dementia and other cognitive declines. This is the primary reason a journey to Mars is so perilous. Astronauts on such a mission would absorb radiation equivalent to getting a full-body CT scan every 5 days for the entire trip, dramatically increasing their lifetime risk of fatal cancer. There is no true escape from it, no place to hide. Even on the International Space Station, which still sits within the protective embrace of Earth's magnetosphere, astronauts are exposed to radiation levels 10 times higher than on the surface. Every moment spent in deep space is a gamble, a roll of the genetic dice where the stakes are the fundamental integrity of your own body. This invisible barrage is a relentless reminder that the universe is not just an empty stage. It is filled with an imperceptible, energetic fury that is constantly, quietly, tearing at the fabric of life itself. And while that invisible radiation constantly assails us, another unseen force, operating on an almost unimaginably grander scale, is pulling our entire galaxy against its will. Imagine you are floating peacefully on a calm, wide river, enjoying the scenery when you slowly realize the current is growing stronger. You're not just drifting, you're being pulled with increasing speed toward a waterfall whose roar you cannot yet hear. On a cosmic scale, this is precisely what is happening to our Milky Way galaxy and every one of its hundreds of billions of stars, including our own sun. We are all caught in a relentless current, being dragged at an incomprehensible speed of 14 million miles per hour toward a specific, mysterious point in the void known to astronomers as the Great Attractor. This isn't just a gentle nudge, it's a violent, unstoppable river of spacetime, and we are caught in its flow. The sheer power required to pull not just our galaxy, but an entire supercluster of galaxies spanning hundreds of millions of light years is beyond staggering. The gravitational source of this cosmic current must be inconceivably massive, a concentration of matter so vast that it defies our current understanding of the universe's structure. Yet, for decades, the true nature of the Great Attractor remained one of astronomy's most profound puzzles, because we couldn't actually see it. From our vantage point on Earth, this monstrous gravitational anomaly lies directly behind the obscuring dust and stars of the Milky Way's galactic plane, in a zone astronomers call the zone of avoidance. It was like trying to identify a distant, roaring beast while standing directly behind a massive, opaque wall. We could feel its pull, we could measure its immense effect, but we were utterly blind to its form. This led to decades of scientific speculation and unease. What could possibly be massive enough to command such motion? Was it a previously unknown, ultra-massive structure, a cosmic defect in the fabric of space-time, or something even more bizarre? The mystery was as profound as it was terrifying, a reminder that some of the universe's most powerful actors can remain completely hidden in plain sight. Their influence felt long before they are ever seen. The terror of being pulled by an unseen force is matched only by the dread of what else might be moving, unseen, through that same darkness. We tend to think of solar systems as stable, orderly places, with planets neatly orbiting their parent star in predictable, clockwork paths. But this comforting image is a cosmic illusion. The galaxy is in fact teeming with orphans, dark and frozen worlds that have been violently ejected from their own stellar families, and now wander the interstellar void alone. These are rogue planets, and their existence is one of the most unsettling realities of our galaxy. Imagine an Earth-sized world, or one even larger than Jupiter, stripped of its sun. There is no sunrise, no daytime, only an eternal, deep freeze night where surface temperatures hover just a few degrees above absolute zero. The only light comes from the faint, unmoving tapestry of the Milky Way above, a panorama of stars that offer no warmth, only a cold reminder of the homes this world lost. These planets are not just rare curiosities. Astronomers now believe they may vastly outnumber the stars in our galaxy, potentially by a factor of 100,000 to 1. That means there could be trillions of these dark, silent wanderers drifting between the stars, a hidden population of ghost worlds far greater than the lit ones we can see. And because they emit no light of their own and reflect no starlight, they are nearly impossible to detect with current technology. They are the ultimate stealth objects, moving through the galaxy's dark currents like submarines in a deep ocean. This leads to a profoundly disturbing possibility. A rogue planet, several times the mass of Jupiter, could be drifting toward our solar system right now, and we would have almost no warning. It wouldn't arrive with a blazing trail or a fiery comet's tail. It would simply be a vast, dark silhouette against the background stars, its presence betrayed only by the subtlest gravitational effects until it was already upon us. The moment it entered the outer reaches of our solar system, its immense gravity would begin to act like a cosmic wrecking ball. The delicate gravitational balance that has kept our solar system stable for billions of years would be shattered. The Oort cloud, that vast, spherical shell of icy planetesimals at the very edge of our sun's influence, would be the first to feel the disturbance. Trillions of comets would be stirred from their stable orbits, sent careening inward like a swarm of bees whose hive has been kicked. As the rogue world plunged deeper, its influence would grow more catastrophic. The orbits of the outer planets, Neptune, Uranus, Saturn, and Jupiter, would be drastically altered. They could be pulled into new, eccentric paths, or in a worst-case scenario, one could be flung out of the solar system entirely, becoming a rogue planet itself. But the true danger would be to the inner solar system, to us. The intruder's gravity would perturb the asteroid belt between Mars and Jupiter, sending a hail of massive rocks onto collision courses with the inner planets. Earth would find itself in a cosmic shooting gallery, facing an extinction-level barrage not seen since the asteroid impact that wiped out the dinosaurs. The rogue planet itself wouldn't even need to hit us. Its gravitational influence alone would be enough to seal our fate. It could alter Earth's own orbit, either pulling us closer to the sun, boiling our oceans away, or flinging us further out, locking our world in a permanent global ice age. The entire architecture of our celestial neighborhood, the very system that made life possible, could be undone by a single, dark, uninvited guest passing through. This isn't a one-in-a-million event. With trillions of these objects adrift in the galactic dark, it is a statistical inevitability over sufficiently long timescales. The universe is not a static museum exhibit. It is a dynamic and sometimes violent arena, and our solar system is not an island, but a participant in a gravitational dance where a misstep from a dark stranger could mean the end of everything. Yet for all the terror of unseen planets and gravitational currents, perhaps nothing is quite as unsettling as a different kind of cosmic phenomenon, not an object, but an overwhelming, soul-crushing absence. If you were to point a telescope toward the constellation of Boötes, the herdsman, you would find a region of space so profoundly empty, so devastatingly vacant, that it has earned the name the Boötes Void. This is not a simple gap between stars. This is a spherical chasm in the universe, a staggering 330 million light-years across. To truly grasp the scale of this emptiness, consider that our entire Milky Way galaxy is a mere 100,000 light-years from end to end. You could line up over 3,000 Milky Way galaxies side by side to span the diameter of this void. Within this incomprehensible volume of space, astronomers have found only about 60 galaxies. A region that, by all rights, should contain thousands of galaxies is instead a near-total vacuum. If our own Milky Way resided at the center of the Boötes void, our knowledge of other galaxies would not have existed until the 1960s. The night sky, beyond our own local stars, would be almost pitch black, offering no hint of the universe teeming with island universes that we know exists. It is a cosmic desert on a scale that defies human comprehension. The existence of such a void forces us to confront a terrifying question about the nature of our reality. What could possibly create such a vast nothingness? The leading theory suggests it is a remnant of the early universe, a giant cosmic bubble formed by the clumping of matter in the primordial soup that followed the Big Bang. As matter gravitated together to form the great walls and filaments of the cosmic web we see today, it left behind these corresponding empty bubbles. But the Boötes void is so exceptionally large that it strains this explanation. It is often called a supervoid, and its sheer scale has prompted more disturbing possibilities. Could it be the result of some ancient, universe-altering catastrophe? Some have even speculated, though it remains firmly in the realm of theoretical physics, that it could be the signature of an incredibly advanced Type 3 civilization on the Kardashev scale, a civilization that has harnessed the power of its entire galactic supercluster. The unsettling hypothesis suggests that such a civilization might have constructed a cosmic megastructure, like a Dyson sphere, around every single star in that volume of space, blocking their light from escaping and making the region appear dark and empty to outside observers. While this is an extreme and highly speculative idea, the very fact that such a colossal emptiness allows for the question is deeply unnerving. It means that when we look at the Boötes void, we are not just looking at a simple absence of matter. We are staring into a profound cosmological mystery. It challenges our understanding of how the universe organizes itself and hints at forces or events we have not yet begun to fathom. This void is a stark reminder that the cosmos is not just randomly scattered with stars and galaxies, but is structured in a way that can include staggering billion light-year-wide pockets of sheer nothingness, making the universe feel less like a comfortable home and more like a vast, unpredictable, and strangely lumpy fabric where existence itself is the exception, not the rule. And while the universe presents us with these vast, physical threats, from invisible radiation to dark, wandering worlds, it also warps the very fabric of reality itself in ways that defy our most fundamental experiences. One of the most mind-bending and personally terrifying consequences of Einstein's theory of relativity is a phenomenon known as time dilation. This isn't a speculative idea. It is a proven, measurable fact of our universe, and it means that time itself is not the constant, universal river we perceive it to be. The rate at which time passes depends entirely on your speed and the strength of the gravitational field you are in. The faster you move through space, the slower you move through time relative to someone who is stationary. This effect is negligible at the speeds of cars or even rockets, but as you approach the speed of light, it becomes profound and chillingly real. The classic thought experiment used to illustrate this is the twin paradox. Imagine a pair of identical twins. One, an astronaut, boards a futuristic spacecraft capable of traveling at an appreciable fraction of light speed, let's say 90%. The other twin remains safely on Earth. The astronaut embarks on a journey to a distant star system, 10 light-years away. From the perspective of the twin on Earth, the round trip to this star and back should take just over 22 years. They live their life, they age, they count down the years, fully expecting their sibling to return 22 years older. But when the spacecraft finally lands back on Earth, the returning astronaut has only aged 10 years. For them, the journey felt like a single decade. They step out of their ship, still youthful, only to be greeted by their Earth-bound twin, who is now 12 years older than they are. The siblings are no longer the same age. One has lived a full dozen years more than the other. The terror here is not in the technology, but in the brutal, personal consequence of this cosmic rule. The astronaut didn't just travel through space, they traveled through time. They effectively leapt 12 years into the future of their own home planet. Every single person they ever knew, parents, friends, spouses, children, would have experienced over 2 decades of life without them. The world they returned to would be irrevocably changed, a place where they are now a relic from a past era. Their children might be older than they are. Their parents would likely have passed away. The culture, the technology, the very memory of their existence would have faded. They would be a ghost in their own life, a living monument to a time long gone, all because of the simple, unchangeable fact that they moved very, very fast. This isn't just a thought experiment. We have to account for time dilation in our everyday technology. The GPS satellites orbiting our planet, for instance, are moving at high speeds relative to the surface of the Earth. Because of their velocity, their onboard clocks actually run slower than clocks on the ground by about 7 microseconds per day. Furthermore, because they are higher up in Earth's gravitational well where gravity is slightly weaker, their clocks run faster by about 45 microseconds per day. The net effect is that they gain about 38 microseconds each day. If the engineers who designed the GPS system did not constantly correct for both of these relativistic effects, the entire system would become useless in a matter of hours, and your phone's navigation would be off by miles. So every time you use a map on your phone, you are relying on the fact that Einstein was right, and that time is truly elastic. This proves that the universe operates on these principles right here, right now. The only thing preventing you from experiencing these effects personally is that you aren't moving fast enough. But the potential is always there, a silent, invisible rule of reality that treats the flow of time not as a constant, but as a variable, making the simple act of travel a one-way journey into the future of everyone you leave behind. That elastic nature of time shows us that the universe operates by rules that are profoundly alien to our daily experience. But there is one cosmic clock whose ticking is both absolute and inescapable for our world. A clock that is counting down to the ultimate end of our planet. Our sun, the gentle, life-giving star that has nurtured our world for 4.6 billion years, is also the instrument of its final destruction. We think of the sun as a constant, an eternal fixture in our sky, but in reality, it is a temporary and dynamic furnace, slowly but surely burning through its finite fuel supply. Every second, deep within its core, the sun fuses about 600 million tons of hydrogen into helium. This process releases the energy that has bathed our planet in warmth and light since the first single-celled organisms stirred in the ancient oceans. But this cannot last forever. The hydrogen fuel in the sun's core will not run out all at once, but the balance of forces will gradually and catastrophically shift. In about 5 billion years, the core will become so dense with the accumulated helium, ash, from billions of years of fusion that hydrogen fusion will be forced to a shell surrounding this inert core. This is the beginning of the end. With the central engine faltering, the delicate equilibrium that has held the sun stable for eons will be broken. The inward crush of gravity will temporarily overcome the outward push of radiation pressure, causing the core to contract and heat up even further. This sudden injection of heat will supercharge the fusion process in the shell around the core, causing the sun to unleash a tremendous surge of energy. This energy will not make the sun hotter. Instead, it will cause its outer layers to expand outward at a terrifying speed, inflating the sun to a monstrous size. Our familiar yellow dwarf star will transform into a red giant, a bloated behemoth so vast that its outer atmosphere will stretch out to engulf the inner solar system. The orbits of Mercury and Venus will be swallowed whole, their rocky bodies vaporized in an instant within the sun's tenuous but searing hot outer layers. And then, the expanding frontier of this stellar inferno will reach Earth. Long before the planet is physically consumed, its fate will be sealed. As the sun grows larger and brighter in our sky, the increasing radiation will begin to bake our world. The delicate carbon cycle that regulates our climate will be utterly overwhelmed. The oceans will start to heat up, first leading to a runaway greenhouse effect much more extreme than anything we can cause today. The water will begin to boil, not in localized patches but across the entire planet, a global rolling boil that will lift the oceans as a thick, suffocating steam atmosphere. That steam will then be broken down by intense ultraviolet light from the dying sun, and the lightweight hydrogen will escape into space, leaving our world forever desiccated. The surface temperatures will rise to over 2,000 degrees Fahrenheit, hot enough to melt lead and glass. The continents will glow a dull red, and the very rocks will begin to vaporize. The Earth will become a hellscape, a literal twin of Venus but on a far more horrific scale. Finally, the expanding photosphere of the red giant sun will likely reach Earth's orbit. There is some debate among astrophysicists about whether the Earth's orbit might have expanded slightly by then due to the sun losing mass, potentially saving it from full engulfment. But even in that best-case scenario, the planet would be orbiting deep within the sun's extended outer atmosphere. The drag from this sparse but present stellar material would slowly but relentlessly pull the Earth inward, spiraling it down into the core within a few thousand years. Whether it is swiftly swallowed or slowly spirals to its doom, the result is the same. Our world will be reduced to a cloud of vaporized metal and rock, its entire history and every trace of life that ever existed on it dissolved back into the elemental components of a dying star. This is not a speculative disaster or a potential cosmic accident. It is stellar evolution. It is the guaranteed, foreseen future of our solar system, written into the fundamental laws of physics. The sun, the source of all life, will ultimately and inevitably become the reaper of that same life. Every sunrise we see is a beautiful reminder that this clock is still ticking, that the star which gives us life is, in its own slow and majestic time, also delivering our death sentence. Even as our own sun promises a slow, majestic end billions of years from now, the universe holds in reserve a form of death that is infinitely more sudden, more violent, and completely random. If the vacuum of space is a silent killer and the expanding sun a slow-motion reaper, then a gamma-ray burst is the cosmic equivalent of a sniper's bullet arriving without warning, striking from across the galaxy, and ending the story of life on Earth in the blink of an eye. These are not mere explosions. They are the single most powerful events known to occur in the universe since the Big Bang itself. For a few fleeting seconds, a single gamma-ray burst can outshine every single star in every single galaxy in the observable universe combined. It releases more energy in that brief flash than our sun will emit over its entire 10 billion-year lifespan. All of that cataclysmic power is focused into two narrow, opposing beams of pure, high-energy radiation, screaming across the cosmos at the speed of light. These terrifying phenomena are born from the deaths of the most massive stars in the universe, or from the mergers of incredibly dense stellar corpses like neutron stars. When a star dozens of times more massive than our sun exhausts its fuel, its core collapses not into a neutron star, but directly into a black hole. As matter plummets into this newborn singularity at nearly light speed, it forms a searingly hot accretion disk. Powerful magnetic fields channel some of the infalling material away from the poles, launching jets that punch straight through the collapsing star's outer layers. These jets, moving at over 99.9% the speed of light, are the particle accelerators that generate the gamma-ray burst. In another scenario, two orbiting neutron stars, locked in a gravitational dance of death, spiral inward over millennia until they finally smash together. This collision also forges a black hole and sends jets of material blasting outward, creating a shorter, but equally devastating, burst of gamma rays. The sheer power involved is almost impossible to comprehend. A typical burst detected from billions of light-years away still delivers more energy to our detectors than the most powerful explosion ever set off by humanity. But the true terror lies not in their distant brilliance, but in their proximity. If one of these cosmic guns were to fire within our galactic neighborhood, say a few thousand light-years from Earth, the consequences would be immediate and apocalyptic. The first sign would be a flash of light in the sky, a second sun appearing for less than a minute, blazing with an intensity that could be visible even in the daytime. But this light would not be the warm, life-giving light of our sun. It would be a wave of high-energy photons capable of breaking apart the very molecules of our atmosphere. The gamma radiation would not reach the surface. Our atmosphere would see to that, but in doing so, it would sacrifice itself. The gamma rays would smash into air molecules, initiating a complex chemical cascade. They would rip nitrogen and oxygen atoms apart, forcing them to recombine into nitric oxide, a compound that acts as a catalyst to destroy ozone. Within hours, our planet's protective ozone layer, the shield that has protected life from the sun's harmful ultraviolet radiation for hundreds of millions of years, would be devastated. Satellite data would show it thinning, then collapsing entirely, leaving the surface of the Earth exposed to the full, unfiltered fury of the sun's UV rays. The aftermath would be a silent, invisible genocide. The ultraviolet radiation levels at the surface would skyrocket to lethal levels, equivalent to standing at the focal point of a giant germicidal lamp. Photosynthetic organisms at the base of the ocean's food web, phytoplankton, would be wiped out, causing a catastrophic collapse of marine ecosystems. On land, plants and animals would suffer severe radiation burns, blindness, and cancers. Creatures that came out during the day would be the first to die, but even nocturnal animals would not be spared, as the entire ecosystem that supported them crumbled away. This is not science fiction. Many scientists now believe that one of the major mass extinction events in Earth's deep past, the Ordovician Silurian extinction around 440 million years ago, which wiped out over 85% of marine species, may have been triggered by a gamma-ray burst. The geological evidence points to a sudden, catastrophic event that destroyed the ozone layer and was followed by a global ice age, a sequence of events that fits the grim profile of a nearby burst perfectly. What makes this threat so uniquely chilling is its randomness and the utter lack of any possible defense. A gamma-ray burst could be happening right now in a distant galaxy, and its light is already on its way to us. We would have no warning until the photons themselves began striking our upper atmosphere. There is no technology we could build, no bunker deep enough to hide in, that could protect the biosphere from such a planet-wide assault. It is a reminder that we exist in a cosmic shooting gallery, where a single random shot from a celestial marksman, fired from clear across the Milky Way, could reset the clock of evolution and end the human story in a single brilliant flash. But for all their cataclysmic power, gamma-ray bursts are merely violent flashes in the cosmic pan, dramatic but localized events. The true, final terror of the cosmos is not a sudden explosion, but a slow, inexorable fade to black that awaits everything, everywhere. This is the ultimate fate of our universe, a concept known as the heat death. It is not a dramatic collision or a fiery implosion, but a quiet, chilling descent into eternal equilibrium, a state of such profound stillness that the very concept of time may lose all meaning. To understand this, we must first grasp the idea of entropy, which is essentially a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of the universe is always increasing. It's a one-way street from order to disorder, from concentrated energy to dissipated, useless heat. Think of the universe like a freshly poured cup of hot coffee. At first, you have a region of high energy, the coffee, and a region of low energy, the room. The energy is concentrated and useful. You can use it to warm your hands, but left alone, the heat from the coffee will inevitably spread out, dissipating into the room until the coffee and the air around it reach the same lukewarm temperature. At that point, the energy is still there, but it's now evenly distributed. It's no longer useful for doing any work. You can't use it to power an engine or warm your hands again. The system has reached maximum entropy, a state of thermal equilibrium where nothing can happen because there are no energy differences to drive any process. Now, scale this simple, everyday observation up to the entire cosmos. Our universe today is that fresh cup of coffee. It is filled with vast energy differences, the searing fury of stellar cores against the near-absolute zero of the void, the intense gravitational potential of black holes, the ordered structure of galaxies and planets. These gradients are what power everything. Stars shine, planets orbit, life evolves. But the universe is expanding, and this expansion is the great engine of its eventual demise. As space itself stretches, these energy gradients are being relentlessly smoothed out. The first stage of this cosmic endgame is the era of stars, which will last for trillions of years, but it is not forever. One by one, over timescales so vast they dwarf the entire current age of the universe, every star in every galaxy will exhaust its nuclear fuel and die. The brilliant, blue-white giants will go first in spectacular supernova. The more common, smaller stars like our Sun will swell into red giants, and then fade away into cooling embers known as white dwarfs. These white dwarfs will themselves slowly radiate their remaining heat away over hundreds of billions of years, cooling until they become cold, black, crystalline spheres of carbon and oxygen, black dwarfs. The universe will grow noticeably darker. The next actors on the stage are the black holes, the most resilient structures in the cosmos, but even they are not immortal. Through a bizarre quantum process at their event horizons predicted by Stephen Hawking, black holes slowly leak radiation and lose mass. This Hawking radiation causes them to evaporate. For a stellar mass black hole, this process takes an almost inconceivable amount of time, a 1 with 67 zeros after it years. But eventually, even the supermassive black holes at the centers of galaxies will evaporate, their final moments punctuated by a faint, final pop of energy. When the last black hole vanishes, the universe will be a sea of subatomic particles and radiation, so spread out by the continuing expansion that a single electron might be the only particle in a volume of space larger than our current observable universe. This is the state of heat death, a cosmos at a uniform, infinitesimally low temperature, just a fraction of a degree above absolute zero. There are no stars, no planets, no galaxies. There is no light, no heat, no sound. The very fabric of space is so vast and empty that particles cannot interact. The fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, have nothing left to act upon. With no energy gradients, no hot and cold to exploit, all physical processes simply stop. Chemical reactions are impossible. Motion is impossible. The universe has reached a state of maximum entropy. It is a perfect, featureless, eternal equilibrium. Time, which we define by change, the ticking of a clock, the orbit of a planet, the beating of a heart, becomes meaningless. In a universe where nothing ever changes, where every point is identical to every other point for all eternity, the idea of before and after ceases to have any significance. It is the ultimate silence, the final darkness, a forever of nothing. This is not a fate that can be avoided or outlived. It is the inescapable conclusion dictated by the fundamental laws of physics as we understand them. Every beautiful nebula, every living world, every conscious thought, every act of love and war in the entire history of existence is but a temporary, flickering spark of order in an ocean of chaos, a brief and brilliant defiance of the silence that will one day claim everything forever. While the ultimate fate of the universe is a distant, abstract terror, A far more immediate and tangible catastrophe could be unfolding right above our heads, one that we are actively creating with our own technology. This is the Kessler syndrome, a doomsday scenario for near-Earth space that turns our orbital environment from a bustling highway into an impassable, high-speed shrapnel field. It's named after a scientist Donald Kessler, who first theorized the possibility back in 1978, and it describes a cascading chain reaction of destruction that, once initiated, could become self-sustaining and irreversible. The premise is deceptively simple. Imagine a single collision between two objects in orbit, a defunct satellite, perhaps, and an old rocket booster. This isn't a slow-motion bump. In low Earth orbit, objects are traveling at roughly 17,500 miles per hour. At that staggering velocity, a collision isn't just an impact. It's a hypervelocity explosion. The two objects don't just break apart. They vaporize, shattering into thousands upon thousands of fragments, from pieces the size of a car door down to tiny, paint flake-sized shards. Each one of these new pieces of debris now becomes a brand new, untracked, and unguided projectile, each carrying the same devastating kinetic energy as a cannonball. This is where the cascade begins. Those thousands of new fragments are now orbiting the Earth, each on its own chaotic path. The probability of another collision has just increased exponentially. One of those fragments might strike another functioning satellite, shattering it and creating tens of thousands more pieces of debris. Those new pieces then go on to cause more collisions, which create even more debris. With each generation of collisions, the cloud of shrapnel grows denser and more lethal, a self-perpetuating storm of metal and ceramic. The terrifying mathematics of the Kessler syndrome shows that after a certain critical density of debris is reached, this chain reaction will continue on its own, even if we never launched another rocket. The cloud would feed on itself, collisions breeding more collisions, until the entire zone of low Earth orbit, the region where the International Space Station resides, where Hubble orbits, and where most of our communication, weather, and spy satellites operate, becomes a swirling, impenetrable shell of razor-sharp shrapnel. The immediate consequences for our modern way of life would be catastrophic and almost instantaneous. The first sign would be the sudden, silent death of our satellites. GPS, the global positioning system that guides everything from your smartphone's map to international shipping and financial transactions, would fail. Weather forecasting would be thrown back to the 1950s, unable to see major storms like hurricanes forming over the ocean until they were practically making landfall. Global communications, including satellite television, phone, and internet for remote areas, would go dark. Military and intelligence agencies would be blinded, their eyes in the sky destroyed. But the horror doesn't stop with losing our technological conveniences. The International Space Station would become a death trap. With the orbital lanes choked with debris, it would be impossible to launch a rescue mission or even a supply ship to the astronauts on board. They would be stranded, their station constantly pelted by impacts, its hull gradually shredded until a critical system failed or a larger piece of debris tore through it, condemning them to a grim fate. Eventually, we would be forced to abandon the station, watching it become just another massive, lifeless target in the growing storm. The most profound long-term consequence, however, is the potential for planetary imprisonment. If the Kessler syndrome were to become fully established in low Earth orbit, launching any spacecraft through that shell would become a suicidal gamble. The spacecraft would have to run a gauntlet of high-speed projectiles with a near certainty of being destroyed. We would be trapped on Earth, our dreams of going back to the Moon, establishing a base on Mars, or venturing out into the solar system extinguished for generations, perhaps for centuries. The window to space would have been slammed shut by our own carelessness, leaving humanity as permanent prisoners on our own planet, staring up at a sky we could no longer reach, surrounded by the glittering, silent wreckage of our own ambition. This is not science fiction. We are already seeing the early warning signs. There have been several major debris-creating events, like the 2009 collision between an active American Iridium satellite and a defunct Russian Cosmos satellite, and China's 2007 anti-satellite weapon test, which alone created over 3,000 pieces of trackable debris. With private companies now launching mega constellations of thousands of satellites, the orbital environment is more crowded than ever before. The Kessler syndrome represents a terrifyingly plausible future, one where humanity's greatest achievements in space become the very weapons that destroy our access to it, creating a cage of our own making just a few hundred miles overhead. And while we've built a cage of potential debris just overhead, one of our most constant celestial companions is in the slow, steady process of leaving us altogether. Our moon, that beautiful, silvery orb that has inspired poets, guided travelers, and stabilized our world since its birth, is quietly drifting away. Every single year, the moon recedes from the Earth by about 1.5 inches. It's a tiny distance, almost negligible in the context of the 240,000 miles that currently separate us. But this gentle retreat is the result of fundamental physical laws, and its long-term consequences are nothing short of world-altering. The mechanism is a celestial tug-of-war driven by gravity and the Earth's rotation. The moon's gravity pulls on the Earth, and this pull is strongest on the side of our planet facing the moon. This gravitational attraction creates a bulge in Earth's oceans, the familiar tidal bulge we experience as high tide. However, because the Earth rotates on its axis faster than the moon orbits around us, our planet's spin actually drags this watery bulge slightly ahead of the direct line between the Earth and the moon. This off-center bulge, in turn, exerts its own gravitational pull on the moon. This extra tug is minuscule, but it acts constantly, and it has the effect of gently pulling the moon forward in its orbit, giving it a tiny boost of energy. In orbital mechanics, gaining energy means moving to a higher, slower orbit. So, as the moon gains this tiny amount of energy from Earth's rotation, it spirals slowly outward. There is a corresponding cost, however. The energy that the moon gains has to come from somewhere, and it is siphoned directly from the Earth's rotational energy. This transfer acts as a perpetual brake on our planet's spin, causing the length of an Earth day to imperceptibly increase. This process is confirmed with incredible precision. Astronomers have been firing lasers at retroreflectors left on the lunar surface by the Apollo missions, and by timing the light's round trip, they can measure the Earth-Moon distance down to a fraction of an inch, confirming the steady annual retreat. Now, the immediate effects of this are utterly negligible to human timescales. Over the course of a human lifetime, the moon will have moved only about 10 feet farther away, and the day will have lengthened by a mere fraction of a second. But when you project this slow, relentless process over billions of years, the future it paints is one of a fundamentally transformed Earth. Let's project forward, say, 600 million years from now. The moon will have receded enough that total solar eclipses, one of nature's most spectacular and perfect coincidences, will be a thing of the past. The moon's apparent size in our sky will have shrunk just enough that it will no longer be able to completely cover the sun's disk. Instead, we would only ever see annular eclipses, where a brilliant ring, or ring of fire, of the sun remains visible around the dark silhouette of the moon. The cosmic ballet that has so perfectly aligned for us will have fallen out of sync, but the truly profound changes come much later. In about 2 billion years, the Earth's rotation will have slowed significantly. A day on Earth will no longer be 24 hours. It might be 25 or even 26 hours long. This might not sound like much, but it begins to disrupt the intricate rhythms that life has evolved alongside. More critically, the moon's stabilizing influence on Earth's axial tilt will have weakened. Right now, the moon's gravitational presence acts like a gyroscope for our planet, keeping the tilt of our axis relatively stable. oscillating gently between about 22.1 and 24.5 degrees over a 41,000-year cycle. This stability is what gives us our predictable and relatively mild seasons. Without the moon's steadying hand, Earth's tilt could become chaotic, wobbling wildly over millions of years, much like the planet Mars does. Mars, with its two small, insignificant moons, has an axial tilt that has varied between 0 and 60 degrees over time. Such extreme variations on Earth would lead to climatic chaos. A greater tilt would mean more extreme seasons, scorching, blistering summers, and unbearably frigid, long winters. A lesser tilt would lead to more uniform global temperatures, potentially disrupting the atmospheric circulation patterns that drive rainfall and create the climate zones we depend on for agriculture. The planet would become a place of violent climatic swings, making it incredibly difficult for complex life, let alone civilization, to thrive. The ultimate, final state of this Earth-Moon system, tens of billions of years in the future, is one of a perfect frozen lock. The Earth's rotation will have slowed so much that a single day will last as long as a single month. The same side of the Earth will always face the Moon, just as the same side of the Moon always faces us today. Our planet would be tidally locked with its companion. From the Earth's surface, the Moon would hang motionless in the sky, a permanent, silent fixture over one hemisphere, while being permanently absent from the other. The transfer of rotational energy would finally cease, and the Moon's retreat would stop, having reached its maximum possible distance. The dynamic, spinning world we know, with its daily cycle of sunrise and sunset, would be gone, replaced by a world with a permanent day side and a permanent night side, each with its own brutal and unforgiving climate. This slow-motion departure of the Moon is a humbling reminder that even the most seemingly permanent features of our sky are transient. The cosmic clock is always ticking, and the gentle forces that shape our lives today are, over the deep abyss of time, carving out a future Earth that would be utterly unrecognizable to us. This ghostly grip of an unseen universe brings us to one of the most profound and unsettling mysteries in all of modern physics: the enigma of dark matter. We've talked about cosmic voids and rogue planets, but those are merely features within the cosmic arena. Dark matter is the very framework of the arena itself, an invisible skeleton upon which the entire visible universe is built. For centuries, we believed that the cosmos was made of the same stuff we are: atoms, molecules, the elements we find on Earth and see in the stars. But we now know with certainty that this is a grand illusion. The planets, stars, galaxies, and nebulae that we can see, touch, and measure with our telescopes constitute less than 5% of the total content of the universe. The rest is dark, with about 27% being this mysterious dark matter, and the remainder an even more bizarre force called dark energy. This means that over 95% of our reality is made of substances that are, for now, completely alien to us. The story of dark matter's discovery begins not with seeing something, but with noticing that something we could see was behaving very strangely. In the 1930s, a brilliant but overlooked Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a vast collection of over 1,000 galaxies. By measuring the velocities of these galaxies as they orbited the cluster's center, he made a shocking observation: they were moving far too quickly. The combined gravitational pull from all the visible matter in the cluster, the stars, gas, and dust, was utterly insufficient to hold the galaxies together. According to the laws of gravity, the cluster should have flown apart eons ago. The only possible explanation was that there was a tremendous amount of additional, invisible mass providing the extra gravitational glue to keep the cluster bound together. Zwicky called this missing mass dunkle materie, or dark matter. For decades, his idea was largely ignored by the scientific community, dismissed as an anomaly or a miscalculation. But the evidence became impossible to ignore decades later when astronomer Vera Rubin, studying the rotation curves of spiral galaxies, found the same bizarre behavior on a smaller scale. Just as planets in our solar system orbit more slowly the farther they are from the Sun, stars at the outer edges of a galaxy should orbit much more slowly than those near the center. Yet Rubin's meticulous work showed that stars at the very fringe of galaxies were orbiting just as fast as those near the core. The visible mass of the galaxy could not account for this. There simply wasn't enough gravity to prevent these high-speed outer stars from being flung off into intergalactic space. The only logical conclusion was that every galaxy is embedded within a gigantic, spherical halo of this invisible matter. A halo that extends far beyond the galaxy's visible edge, its gravitational pull whipping the stars along on their unexpectedly fast trajectories. So what is this stuff? We know it exists because of its gravitational influence. We can literally map its distribution by watching how its gravity bends the light from more distant galaxies, an effect called gravitational lensing. But beyond that, it is utterly elusive. It does not emit, absorb, or reflect any form of light or electromagnetic radiation. It is completely transparent. You could have a block of dark matter the size of a mountain right in front of you, and it would be utterly invisible and undetectable to your eyes or any conventional camera. We know it's not made of the same protons, neutrons, and electrons that constitute normal matter, because if it were, it would interact with light. This has led physicists to propose a zoo of hypothetical particles, with the leading candidate being a class of particles known as WIMP, or weakly interacting massive particles. These particles would be heavy, and as their name suggests, interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to catch. The terrifying implication here is not just that we don't know what dark matter is, but that it forces us to accept that the universe we perceive is just the tip of a vast, invisible iceberg. Every time you look up at the night sky, you are not seeing the true structure of the cosmos. You are seeing the luminous tracers, the glittering decorations, hung upon a hidden scaffold of dark matter. Our own Milky Way galaxy is not just a spinning disk of stars. It is a colossal sphere of this invisible substance, weighing perhaps 30 times more than all the visible stars and gas combined. We are living inside a ghost, our every movement, our planet's orbit, our sun's journey around the galactic center, all dictated by the gravitational pull of something we cannot see, touch, or comprehend. It is the ultimate cosmic puppet master, and we are only now beginning to feel the strings. And if dark matter represents the invisible framework of our reality, then the silence that surrounds us speaks to an even deeper cosmic mystery. Given the sheer scale of the universe with its trillions of stars and likely even more planets, the numbers alone suggest we should not be alone. The Milky Way galaxy is over 13 billion years old, and our Sun is a relative newcomer. That means there has been ample time, countless opportunities, for other intelligent civilizations to arise, to flourish, and to spread across the galaxy. With even conservative estimates, the galaxy should be teeming with life, its lanes buzzing with interstellar traffic. And yet, when we point our radio telescopes to the heavens, we are met with a profound and unsettling silence. This glaring contradiction between the high probability of extraterrestrial life and the complete lack of any evidence for it is known as the Fermi paradox, named for the physicist Enrico Fermi, who, during a casual conversation in 1950, famously asked, "But where is everybody?" The solutions to this paradox are, in many ways, more terrifying than the silence itself. One of the most chilling explanations is the concept of the Great Filter. This theory suggests that the evolution of life from its basic origins to a space-faring, galaxy-colonizing civilization requires the passage through a series of incredibly difficult evolutionary and technological steps. The Great Filter is that one, nearly insurmountable barrier that prevents almost every species from progressing to the next stage. It could be an event or a challenge so difficult that it statistically wipes out the vast majority of life, before it can become visible on a galactic scale. The terrifying question for us is, where is this filter located? Is it safely behind us? A hurdle that life on Earth somehow managed to overcome against all odds. Perhaps the filter was the transition from single-celled prokaryotic life to more complex eukaryotic cells, a jump that took over 1 billion years to happen here and might be exceptionally rare. Or maybe it was the development of multicellular life itself. If the filter is in our past, it would mean we are a cosmic miracle, one of the very few, if not the only, intelligent species to have made it this far. The more horrifying possibility is that the great filter lies ahead of us in our future. This is the scenario that should give every human being pause. It proposes that there is a predictable, perhaps inevitable, point in a civilization's technological development that leads to its own destruction. Every other civilization that has reached our level of advancement has already encountered this filter and failed to pass through it. What could this future filter be? There are several grim candidates, all born from our own technological prowess. It could be the development of advanced artificial intelligence that becomes uncontrollable and turns against its creators. A scenario often explored in science fiction, but taken very seriously by many technologists and philosophers. It could be the engineering of a superbug, a genetically modified pathogen with a mortality rate that wipes out its creators before it can be contained. Most classically, it could be the discovery of nuclear fission, providing a civilization with the power to utterly destroy itself in a final, global war. The silence of the cosmos, in this interpretation, is not a sign of our solitude, but a graveyard. It is the evidence that intelligence is a tragic, self-limiting phenomenon, a cosmic flame that burns brightly for a moment only to consume itself. We look up at the silent stars not as neighbors we have yet to meet, but as tombstones for civilizations that are already long gone. Our continued existence may not be a sign of our success, but merely a measure of our lateness to the party, a party that ended in catastrophe for everyone else, and a fate that may still be waiting for us just around the next technological corner. But the silence of the cosmos is not always empty. Sometimes it is broken by the solitary, high-speed flight of a cosmic exile. We've discussed rogue planets, dark and frozen worlds cast adrift from their stars. Now, consider an even more powerful and terrifying phenomenon: stars themselves being violently evicted from their galactic homes. These are hypervelocity stars, and they are some of the fastest solitary objects in the entire universe, hurtling through the intergalactic void at speeds exceeding 1 million miles per hour. To put that incomprehensible velocity into perspective, at that speed, you could travel from the Earth to the Moon in just under 15 minutes. The origin story of these stellar projectiles is as dramatic as their speed. They are born from the most chaotic and violent environment a galaxy can offer: the immediate vicinity of a supermassive black hole. At the heart of most large galaxies, including our own Milky Way, resides one of these gravitational monsters, containing the mass of millions or even billions of suns compressed into a single point. When a binary star system, two stars orbiting a common center of gravity, ventures too close to this cosmic beast, a gravitational slingshot event of catastrophic proportions can occur. The black hole's immense tidal forces can tear the binary pair apart. One of the stars is captured by the black hole, falling into a tight, doomed orbit. The other, in a demonstration of Newton's third law of motion, is flung away at a staggering fraction of the speed of light, ejected from its galaxy entirely as if shot from a cannon. This star, still burning with its own nuclear fire, then begins an eternal journey through the black emptiness between galaxies, a lone beacon with no destination. The existence of these stars is a confirmed and observed reality. Astronomers have identified dozens of them streaming out of our own Milky Way, their trajectories traced back directly to the galactic center. They serve as a stark reminder of the titanic forces at play in what we often think of as the serene, structured environment of a galaxy. But the true terror of hypervelocity stars is not their lonely voyage. It is the potential consequence of a close encounter with our own solar system. Our Sun, with its family of planets, orbits the galactic center in a relatively quiet, stable suburb, far from the violent downtown core. We are shielded by distance. But the galaxy is a dynamic place, and the paths of these stellar bullets are unpredictable over millions of years. What if one were headed our way? A hypervelocity star would not arrive with a bright, warming light like a second sun. Long before it entered the planetary zone of our solar system, its gravitational influence would begin to act like a cosmic bulldozer, plowing through the delicate gravitational harmony that has persisted for billions of years. The Oort cloud, that vast reservoir of icy bodies at the solar system's outer edge, would be the first to feel the disturbance. Trillions of comets would be stirred from their stable orbits and sent careening inward, creating a storm of potential impacts that could last for millions of years, bombarding the inner planets and threatening any life on their surfaces. As the star drew closer, its gravity would begin to directly tug on the outer planets. The gas giants Jupiter, Saturn, Uranus, and Neptune, with their massive orbits, would be the most susceptible. Their stable, circular paths could be warped into highly elliptical ones, or in a worst-case scenario, one could be ripped from the Sun's grasp entirely, becoming a rogue planet cast into the darkness. This alone would be a disaster of cosmic proportions, but the real danger would be the perturbation of Earth's own orbit. Our planet exists in the Goldilocks zone, where temperatures are just right for liquid water and life. This position is not a fixed, immutable law. It is a precarious balance. The gravitational nudge from a passing hypervelocity star, even one that didn't come closer than the orbit of Pluto, could be enough to alter Earth's trajectory. It could push us slightly inward, toward the Sun, initiating a runaway greenhouse effect that would boil our oceans and turn our world into a scorching hellscape like Venus. Or it could pull us outward, away from the Sun's warmth, slowly freezing the planet solid and encasing it in a global ice sheet miles thick. The star wouldn't need to collide with us. It wouldn't even need to be visually impressive in our sky. Its invisible hand of gravity, reaching across billions of miles, would be more than enough to permanently extinguish all life on Earth, leaving our world a barren rock while the star itself continued on its relentless, indifferent journey into the void. This underscores a chilling reality. The stability of our solar system is an illusion maintained by isolation. We are safe only so long as nothing massive and fast-moving passes through our neighborhood, and the galaxy is full of such potential interlopers, each one a silent, high-speed reminder of how quickly cosmic order can descend into chaos. This invisible framework of dark matter is not a formless cloud. It has a specific, breathtaking architecture, a structure so vast it makes individual galaxies look like mere specks of dust. This is the cosmic web, the largest known pattern in the universe. Picture, if you can, the universe on its grandest scale not as a random scattering of galaxies, but as a colossal, three-dimensional spiderweb, with filaments of dark matter stretching across billions of light years like luminous threads of dew in the morning sun. These filaments are the superhighways of the cosmos, and at their intersections where the gravitational pull is strongest, galaxies cluster together in massive, dense knots. But between these brilliant strands of light and matter lie the true dominance of space, the voids. These are not small, empty patches, but staggering, billion-light-year-wide spherical deserts of near-total nothingness. The Boötes void we discussed earlier is just one example. The cosmos is filled with these gaping chasms. The cosmic web is a structure of contrast so extreme it defies human intuition. Dense, glittering walls of galaxies separated by volumes of emptiness so vast that if you were placed at the center of one, you would see absolute blackness in every direction, with no galaxy visible to the naked eye. To truly grasp the scale of this structure and our place within it, we need to pull the camera back, far beyond our own Milky Way. Our galaxy is not floating in isolation. It is part of a small, local group of about 54 galaxies, including our great spiral neighbor, Andromeda. This local group feels like our entire cosmic neighborhood. But this neighborhood is itself just one tiny, insignificant part of a much larger structure known as the Laniakea supercluster. The name Laniakea means immense heaven in Hawaiian, and it is a fitting title. This supercluster is a gravitational watershed, a continent of galaxies 500 million light-years across, containing over 100,000 individual galaxies all flowing together in the cosmic current. Our Milky Way resides not in a central, important city within this continent, but out on a quiet, suburban filament, a spur of the supercluster. And the Laniakea supercluster itself is just one thread in the grander cosmic web. We are not at the center of anything. We are residents of a quiet, unremarkable street in an endless metropolis of galaxies. A metropolis where the buildings are separated by deserts of emptiness larger than the human mind can conceive. This cosmic geography reveals a terrifying truth about our place in the universe. We are profoundly, inescapably isolated. The distances between these superclusters across the voids are so immense that they present a barrier that may be fundamentally unbridgeable, even for a theoretically advanced civilization. The nearest major supercluster to Laniakea is the Shapley supercluster, over 650 million light-years away. The space between them is the Great Void. Even if we could travel at the speed of light, a journey to our nearest major cosmic neighbor would take longer than the current age of our planet. This cosmic web, for all its beautiful structure, is also a cage. It means that the vast majority of the universe is forever out of our reach, not because of technological limitations, but because of the fundamental architecture of space-time itself. We are on an island in an ocean of nothing, and the other islands are so distant we can only see their lights from across an eternal, expanding sea. The cosmic web is the ultimate map of existence, and it shows us that we live in a universe that is mostly empty. A sobering reality that makes our local galaxy group feel less like a home and more like a solitary life raft adrift in an infinite, dark ocean. While the dangers of rogue planets and gamma-ray bursts are terrifying in their cosmic scale, a far more immediate and historically proven threat orbits much closer to home, hiding in the plain sight of our own solar system. This is the ever-present risk of a catastrophic asteroid impact, a danger not of theoretical physics, but of celestial mechanics and grim geological history. We need only look to our own planet's past to find the blueprint for such a disaster. 66 million years ago, a seemingly ordinary day for the dinosaurs was shattered when a mountain-sized rock, estimated to be about 6 miles wide, slammed into what is now the Yucatan Peninsula in Mexico. This was the Chicxulub impactor. It wasn't just a big rock falling from the sky. It was an event that released energy equivalent to billions of the atomic bombs dropped on Hiroshima. The initial impact created a fireball so immense it incinerated everything within hundreds of miles and triggered a global firestorm. But the immediate blast was only the beginning of the end. The impact vaporized trillions of tons of rock, hurling it high above the atmosphere. As this superheated debris rained back down across the entire planet, it heated the air to the temperature of an oven, literally broiling any life that had survived the initial conflagration. Then came the long winter. The dust and soot thrown into the upper atmosphere encircled the globe, blocking the sun's light for months, perhaps even years. Photosynthesis ground to a halt, collapsing the base of the food web. The dinosaurs, who had ruled the Earth for over 150 million years, were wiped out, along with 75% of all plant and animal species. This wasn't a freak accident. It was a demonstration of the brutal efficiency with which a random piece of space rock can reset the evolutionary clock. The chilling reality is that the cosmic shooting gallery that produced the Chicxulub impactor is still active today. Our solar system is filled with millions of asteroids, the leftover building blocks from its formation. Many of these orbit peacefully in the main asteroid belt between Mars and Jupiter, but a significant number have orbits that bring them into Earth's neighborhood. These are known as near-Earth objects, or NEO, and NAS, a Planetary Defense Coordination Office, actively tracks more than 30,000 of them. Using a network of ground-based telescopes, astronomers constantly monitor these objects, calculating their trajectories centuries into the future to assess their potential risk. This system has had some success. In March of 2023, a small asteroid, roughly the size of a swimming pool, was detected just days before it harmlessly exploded over the English Channel. While this was a testament to our growing detection capabilities for smaller objects, it also highlights a terrifying gap in our knowledge. For every asteroid we track, there are countless more we have not yet found. Current estimates suggest we have only identified about 40% of the asteroids larger than 140 meters in size, objects large enough to devastate an entire region or continent. The smaller, yet still dangerously potent, objects are even more elusive. A rock just 50 meters across, similar to the one that caused the Tunguska event in Siberia in 1908, could flatten a city, and we have likely discovered less than 10% of this population. The true terror of an asteroid impact lies not just in the possibility, but in the potential for minimal warning. While Hollywood often depicts a years-long scramble to save the planet, the more plausible scenario for a civilization-ending impact is one of devastatingly short notice. The solar system is a vast, dark place, and an asteroid on a collision course with Earth could be approaching from the direction of the Sun, completely hidden in its glare, until it is far too late to do anything but watch. In 2019, a 100-meter-wide asteroid named 2019 OK passed within 45,000 miles of Earth, a cosmic hair's breadth, and it was detected just days before its closest approach. It had been approaching from the sunward direction, completely blinding our telescopes. Had its trajectory been slightly different, it would have impacted with the force of a large nuclear weapon. This underscores a sobering vulnerability. Our planetary defense is not yet a complete shield, but more of a partial monitoring system with significant blind spots. The effort to find and catalog every potentially hazardous object is a race against time, a slow, methodical search for needles in a haystack the size of the inner solar system, where a single overlooked object could carry the same message for humanity that the Chicxulub impactor delivered to the dinosaurs. And that profound silence we encounter in the cosmic web extends far beyond the voids between galaxies. It is a fundamental property of the vacuum of space itself. We are conditioned by movies and television to expect a soundtrack for the universe, to hear the roar of a starship's engines or the explosive boom of a supernova. But the reality is infinitely more chilling. Space is a near-perfect vacuum, and sound, as we understand it, cannot travel through a vacuum. Sound is a mechanical wave. It needs a medium to propagate, something for its vibrations to push against, like air molecules or water. In the emptiness between stars and planets, there are simply not enough particles packed together to carry those vibrations. This means that the most violent, energetic, and catastrophic events in the cosmos occur in absolute, deafening silence. Imagine witnessing a supernova, the death of a massive star, from a safe distance. You would see an unimaginable fireball erupt, outshining its entire host galaxy for weeks. You would feel the heat from the radiation on your skin, and if you were too close, your body would be bathed in a lethal wave of X-rays and gamma rays. But you would hear nothing. The star's outer layers, blasted outward at millions of miles per hour, would expand in a cataclysmic shockwave, but the propagation of that violence would be utterly noiseless. Two galaxies could collide in a billion years, long gravitational dance, their spiral arms tearing each other apart, stars being flung into the void, and colossal clouds of gas colliding and igniting new stellar nurseries. From within, it would be a visual spectacle of cosmic proportions, a ballet of destruction and creation on a scale that dwarfs all human comprehension. Yet, the entire event would unfold in perfect, profound quiet. An asteroid striking an airless moon doesn't go crunch or boom. It simply makes a flash and a plume of dust, its kinetic energy converted to light and heat without a single whisper of sound. This disconnect between the visual fury and the auditory void creates a deep, psychological dissonance. Our brains are wired to associate massive, violent forces with equally massive sounds. The crack of thunder, the rumble of an earthquake, the blast of an explosion. These sounds give the event weight and visceral impact. They make it feel real and immediate. To witness such power operating in complete silence feels unnatural, almost dreamlike. It strips the event of its emotional resonance for a human observer and replaces it with a cold, detached observation. This silence is the true voice of the cosmos. It is not a peaceful quiet, but the silence of absolute indifference. It tells us that the universe is not putting on a show for us. These colossal events are not meant to be witnessed or heard. They simply are. The vacuum is the ultimate insulator, ensuring that the death cries of stars and the collisions of worlds are private affairs, their monumental energies dissipating as light and radiation, but never as sound. It reinforces our status as insignificant observers on a tiny rock, privy to the sights of the cosmos, but forever deaf to its most powerful moments, left to watch the violent beauty of the universe play out as a silent film on an infinite screen. We have explored the silent killers of radiation and the ghostly pull of dark matter. But there is a far more visceral and gruesome fate waiting in the hearts of galaxies, a force that doesn't just kill, but utterly unravels you. At the center of our own Milky Way, a seemingly placid and dark region of space known as Sagittarius holds a secret. This is not an empty void. It is a supermassive black hole, containing the mass of over 4 million suns crushed into a single point of infinite density. We often talk about black holes as having such strong gravity that not even light can escape. But this abstract concept hides a process of destruction so bizarre and personal that it has its own name: spaghettification. To understand this, you have to think about gravity not as a single force pulling you down, but as a difference in pull between different parts of your body. When you stand on Earth, the gravity pulling on your head is only infinitesimally weaker than the gravity pulling on your feet. But near a black hole, the gravitational gradient is so incredibly steep that the difference becomes catastrophic. If you were to fall toward a stellar mass black hole, this process would happen violently and quickly. But with a supermassive giant like Sagittarius A, the experience would be prolonged and even more terrifying because its event horizon, the point of no return, is so much larger. You could cross it without immediately noticing anything amiss, but the tidal forces would have already begun their work long before that invisible boundary. As you approach, feet first, the pull of gravity on your feet is exponentially stronger than the pull on your head. This difference in force begins to stretch you. It's not a gentle tug, it's an irresistible, cosmic pulling apart. Your body would be elongated, thinning out like a piece of warm taffy. At the same time, the gravitational forces from the sides would be compressing you inward, squeezing you from all directions. You are simultaneously being stretched lengthwise and crushed sideways. The result is that your entire body is shaped into a long, thin stream of atoms, a single, human-shaped noodle of matter spiraling toward the darkness. This isn't just a dramatic visual, it's the fundamental physics of extreme gravity. Every molecule in your body would be torn from its neighboring molecules. Your bones, your muscles, your organs would all be separated into a stream of individual atoms. You wouldn't just die, you would be systematically disassembled. your very atomic structure unmade by a force that treats a human body as carelessly as a child pulling apart a cotton ball. And this entire, horrifying transformation would happen while you were still fully conscious and aware, watching your own body distort into an impossible shape against the backdrop of a warped and twisted universe. The spaghettification process near a supermassive black hole is slower and more methodical than near a smaller one, meaning you would have a front-row seat to your own dissolution, a silent, screaming journey into a stream of fundamental particles, a fate that illustrates with brutal clarity that the universe contains forces not merely hostile to life, but utterly indifferent to its form. Reducing the most complex structures into their simplest, most silent components. But for all the terror of being torn apart by a black hole or vaporized by an asteroid, these are localized disasters. The ultimate fate of the entire cosmos, dictated by a force even more mysterious than dark matter, is a slow, cold, and lonely unraveling of reality itself. For most of the 20th century, astronomers believed the universe's expansion was a relic of the Big Bang, a single, initial explosion that was gradually slowing down over time due to the collective gravitational pull of all the matter in the cosmos. It was assumed that this expansion would eventually coast to a halt, or perhaps even reverse in a big crunch. Then, in the late 1990s, two independent teams of scientists made a discovery so shocking it fundamentally rewrote our understanding of cosmic destiny. By observing distant supernova exploding stars used as cosmic mile markers, they found that the universe is not expanding at a steady rate, nor is it slowing down. It is accelerating. The fabric of space itself is stretching faster and faster with each passing moment, as if some invisible, repulsive force is steadily overpowering gravity itself. This mysterious culprit was dubbed dark energy, and it constitutes about 68% of the total energy content of the universe, making it the dominant force in the cosmos. The implications of this accelerated expansion are not just mathematical curiosities. They point toward a future of profound and utter isolation. Imagine each galaxy as a lone ship on an impossibly vast, dark ocean. Right now, we can see the lights of other ships, other galaxies, scattered across the cosmic sea. But because space itself is stretching, the distance between our galaxy and all others is increasing. As the expansion accelerates, those distant lights will begin to fade. First, the most far-flung galaxies will have their light stretched so far that it shifts into invisible radio waves, and then their light will be stretched so much that the wavelength becomes effectively infinite, and they simply vanish from our view. This will happen not because the galaxies are moving away through space, but because the space between us and them is being created faster than light can traverse it. One by one, the galaxies will wink out of our observable universe, their light never able to reach us again. In a future tens of billions of years from now, any astronomers in the Milky Way will look out into the sky and see nothing. The Andromeda Galaxy and a few dozen other small galaxies in our local group will have long since merged with us into one giant, aging elliptical galaxy. But beyond that, the cosmos will be an in-kai, absolute black. All evidence of the Big Bang, the cosmic microwave background radiation, will have redshifted into undetectability. There will be no clues that a vast, vibrant universe of trillions of other galaxies ever existed. Our island galaxy will be a solitary, floating tomb in an endless, expanding void, a single, fading ember in an infinite freezer. The nature of dark energy itself is perhaps the greatest unsolved problem in physics. The leading theory suggests it is a property of the vacuum of space itself, a constant energy density that causes a repulsive gravitational effect. But its measured value is so inexplicably small and yet so dominant that it has been called the worst theoretical prediction in the history of physics. Other, more radical ideas propose that our understanding of gravity is incomplete on cosmic scales, or that dark energy is a dynamic field that could change over time, potentially leading to an even more violent end for the cosmos, a big rip where the accelerating expansion eventually tears apart galaxies, stars, planets, and even atoms themselves. For now, the accelerating universe stands as a chilling final verdict. It means that the cosmos is not only hostile and dangerous in the present, but its very fundamental laws are engineered for a future of eternal solitude and darkness, a silent, lonely conclusion to the grand story of everything. But for all the grand, slow-motion terrors of dark energy and the heat death, there exists a theoretical threat that operates on a scale so fundamental, it makes even the most violent supernovas seem insignificant. This is the concept of the false vacuum, a hypothesis from the cutting edge of quantum field theory that suggests our entire universe is living on borrowed time, perched precariously on a cliff edge of reality itself. To understand this, we need to think of the universe not as a collection of stars and galaxies, but as a field of energy, a kind of invisible substrate that exists everywhere, even in the deepest, emptiest voids of space. This energy field is thought to have a value, much like a ball sitting in a valley represents a state of low energy. For our universe to be stable and permanent, this ball would need to be resting at the absolute lowest possible energy state, what physicists call the true vacuum. This would be the most stable, settled state of reality, a place where the laws of physics are fixed and eternal. The terrifying possibility raised by some of our best models is that we are not in this true vacuum. Instead, our universe might be in a false vacuum, a metastable state. Imagine that ball isn't in the deepest valley, but is instead resting in a small dip on the side of a much larger valley. It seems stable for now. It has been sitting there for 13.8 billion years, but it's not in its ultimate, lowest energy state. It's perched. And if given enough of a nudge, it could roll out of that small dip and down into the far deeper valley below. In this analogy, that nudge could be almost anything: a random quantum fluctuation, a particularly high-energy particle collision in a particle accelerator, or an event in the distant cosmos. If it happens, it would trigger a catastrophe unlike any other. At that point in space, the universe would transition to the true vacuum state. This new state would have fundamentally different laws of physics. The constants we take for granted, the strength of gravity, the mass of an electron, the speed of light, could be completely different. This transition wouldn't just change things, it would erase the old reality and replace it with a new one. And once this bubble of true vacuum appears, it would begin to expand. Crucially, it would expand at the speed of light, not through space but by rewriting space itself. The wall of this bubble would be a wave of total transformation, a boundary beyond which our familiar universe simply ceases to exist. There would be no warning that could outrun it. Since it moves at light speed, the first sign of its arrival would be the transformation itself. One moment, our region of the cosmos exists. The next, it is gone, replaced by a new reality with properties we cannot possibly predict. Chemistry as we know it would be impossible. Atoms could not form. The very concept of matter might be meaningless. Everything, every planet, every star, every living being, every memory would be unmade in an instant, not into stardust, but into something entirely and fundamentally other. What makes this possibility so uniquely chilling is its combination of randomness, inevitability, and totality. It could have been triggered a billion years ago in a galaxy far, far away, and the bubble of destruction could already be on its way to us, its wall of nothingness traveling at light speed through the dark. We would have no way of knowing it was coming until it was literally upon us, as any signal that could warn us would be limited to the speed of light, arriving at the exact same moment as the bubble itself. Or the trigger could happen tomorrow, right here on Earth, from a random quantum event so rare it was statistically unlikely to happen in the entire lifetime of the universe, yet it happens now. The false vacuum decay is the ultimate cosmic reset button, a threat that doesn't just destroy life. but renders the very physical laws that allowed for life to exist in the first place null and void. It suggests that the stage upon which all other cosmic dramas play out is itself unstable, and that the greatest terror may not be something in the universe, but the fragile nature of the universe itself. Yet even as we contemplate the potential for a false vacuum collapse that could rewrite reality itself, we can look up and actually see the faint, ghostly echo of our universe's birth. An echo that also serves as a constant, chilling preview of its ultimate demise. This is the cosmic microwave background radiation, and it is the oldest light in existence. It fills every cubic inch of the cosmos, a silent, shimmering backdrop to everything we will ever know. To understand it, we have to travel back in time almost to the very beginning, to a point roughly 380,000 years after the Big Bang. Before this moment, the universe was an opaque, searingly hot plasma, so dense that light particles, photons, were trapped in a constant pinball game with free electrons, unable to travel in a straight line. The universe was a brilliant, blinding fog. But as it expanded and cooled, it reached a critical temperature about 3,000 degrees Celsius, where electrons could finally combine with atomic nuclei to form the first stable atoms, mostly hydrogen and helium. In that instant, the fog lifted. The photons, which had been trapped for eons, were suddenly set free, released to travel across the cosmos. This moment of liberation, the moment the universe became transparent, is the source of the light we now detect as the cosmic microwave background. It is the flash from the birth of the cosmic void, and it has been traveling for 13.8 billion years, stretched and cooled by the relentless expansion of space itself. What we detect today is no longer a brilliant flash, but a faint, cold whisper. That initial light, once as bright as the surface of a star, has been stretched by the expanding universe from visible light into the microwave part of the spectrum. Its temperature has plummeted from thousands of degrees to just 2.7 degrees above absolute zero. If you could see microwave radiation with your eyes, the entire night sky would not be black, but would glow with a uniform, ethereal light, a testament to that primordial fire. We can capture this glow with specialized radio telescopes, and the map it creates is the most important baby picture of the universe we will ever have. It shows tiny, minuscule fluctuations, regions that are ever so slightly warmer or colder than the average. These tiny ripples are the seeds of all future structure. The slightly denser, warmer spots are the gravitational wells that would, over billions of years, pull in more and more matter, eventually forming the galaxies, galaxy clusters, and the vast cosmic web we see today. In a very real sense, we are looking at the blueprint for existence, but this beautiful, foundational glow has a far more somber and terrifying identity. It is not just the afterglow of creation, it is the universe's funeral shroud. This radiation is the definitive proof that the universe had a hot, dense beginning, and the laws of thermodynamics dictate its ultimate end. The cosmic microwave background is the universe's primary source of heat, as pitiful as it is, and it is cooling. As the expansion of space continues, this radiation will be stretched to even longer wavelengths and lower energies. Billions of years from now, it will have cooled from its current 2.7 Kelvin to perhaps just 1 degree above absolute zero. Trillions of years in the future, it will be so cold and its photons so low energy that it will be virtually undetectable, even with technology far beyond our own. It will have faded into the background radio static of the cosmos, and then into nothingness. This process is irreversible. The heat from the Big Bang is the universe's finite reservoir of usable energy, and it is being dissipated into an ever larger volume, driving the cosmos toward the ultimate equilibrium of heat-death. The cosmic microwave background is therefore a constant, inescapable reminder. It is the dying ember of the initial fireball, still visible, but cooling with every passing moment. It tells us that the universe is not in a steady state. It is a one-way journey from a state of intense, concentrated energy to a state of cold, dissipated uniformity. Every time a cosmologist measures this faint glow, they are not just looking at the birth of the cosmos. They are taking the temperature of a dying patient, watching the final embers of creation slowly, inexorably, fade to black. We have been charting the terrifying expanse of space, confronting forces that could shatter worlds and fates that could erase entire universes. Yet, there is a different kind of terror, one born not from violence, but from the sheer, incomprehensible weight of deep time. We speak of the universe being 13.8 billion years old, but that number is so vast it slides off the human mind without leaving a mark. To truly feel its weight, we must shrink it down to a scale we can grasp. Imagine compressing the entire history of the universe into a single calendar year, with the Big Bang striking at the very first second of January 1st. In this cosmic year, each month represents a little over 1 billion years. Our Milky Way galaxy might form sometime in January or February. The Sun and Earth don't even appear until early September. Life on Earth spends months as nothing more than single-celled organisms. The first complex animals with skeletons and shells emerge around December 17th. The dinosaurs rule the planet from December 26th until the evening of December 30th. The entirety of recorded human history, from the first civilizations to the pyramids, to Rome, to the modern day, fits into the last 60 seconds of December 31st. Every war, every empire, every discovery, every human life that has ever been lived, all unfolds in that final, fleeting minute before midnight. This perspective is not just humbling, it is existentially jarring. It reveals that we are not just latecomers to the cosmic party. We are guests who have arrived in the very last fleeting moments, long after the main events have concluded. But here is the truly chilling part of this timeline, the part that most discussions of the universe's age conveniently ignore. We think of the cosmos as a place of brilliant galaxies and shining stars, but this vibrant era is merely a brief, brilliant flash in an otherwise endless and dark eternity. The stellar era, the time when new stars are actively being born and lighting up the cosmos, is not the main event. It is the opening act. Current models of stellar evolution suggest that the last new stars will ignite in about 100 trillion years. After that, the star-forming gas in galaxies will be exhausted, and the universe will enter its long, middle age, the degenerate era. This period will last for trillions upon trillions of years, a timespan that makes the current age of the universe seem like the blink of an eye. During this unimaginably long epoch, the universe will be populated by the fading remnants of its former glory. The sky will no longer be dotted with brilliant blue giants or warm yellow suns. Instead, the only sources of light will be the cooling embers of dead stars, white dwarfs which will slowly dim from white to red to black over hundreds of billions of years, and neutron stars which will pulse with ever-weakening beats until they too fall silent. Brown dwarfs, failed stars that never ignited, will occasionally collide, flaring up for a brief moment to create a final, lonely red dwarf star. But these will be rare and temporary events in an otherwise darkening cosmos. This is not the end of the timeline, but merely the beginning of the end. The degenerate era will eventually give way to the black hole era, where only these gravitational monsters retain any significant energy. And finally, after timelines so vast they are essentially meaningless to us, to the dark era, a forever of nothingness where even black holes have evaporated. The terrifying takeaway is this: the universe we know and observe, the one filled with light and structure and the potential for life, represents far less than 1% of its total lifespan. We exist in a fleeting, golden moment, a sliver of cosmic dawn nestled between the primordial fire and an endless, cold night. The overwhelming majority of the universe's existence, 99.99% of its entire timeline, will be a cold, dark, and silent graveyard, a fossil of the vibrant era we are so fortunate to witness. This fact reframes our entire existence. We are not living in a universe in its prime. We are living in its brilliant, spectacular, and tragically brief youth, born just in time to see the last of the lights before the eternal darkness sets in. While our sun provides the energy that makes our world livable, it also possesses a temper, capable of unleashing storms of such power that they could, in a single day, undo centuries of technological progress. This isn't a distant, speculative threat like the heat death of the universe. It is a documented historical event that is guaranteed to happen again. The most famous example is the Carrington event of 1859. In the early hours of September 1st, British astronomer Richard Carrington observed an intense white light flare erupting from a massive group of sunspots. What followed less than 18 hours later was a celestial light show of unprecedented ferocity. Telegraph systems, the high-tech communication network of the Victorian era, went haywire worldwide. Operators received severe electric shocks, telegraph paper spontaneously caught fire, and messages could be sent even with the power supplies disconnected, powered solely by the currents flowing through the Earth's atmosphere induced by the storm. Skies as far south as the Caribbean erupted in auroras so brilliant that people could read newspapers by their light in the middle of the night. It was a breathtaking spectacle, but one that caused relatively minor damage only because the world of 1859 was not yet wired for electricity. A similar event striking our planet today would not be a beautiful light show. It would be the single greatest technological catastrophe in human history. The mechanism is a coronal mass ejection, or CME, which is a colossal bubble of billions of tons of solar plasma, threaded with a powerful magnetic field, blasted from the sun's corona at speeds of several million miles per hour. When this magnetized cloud is aimed at Earth, it interacts with our planet's own magnetic field in a violent and chaotic dance. This interaction induces massive, fluctuating electrical currents in the ground itself, a phenomenon known as geomagnetically induced currents. In the 1800s, these currents found their way into the only long-distance conductors available, telegraph wires. Today, our planet is enmeshed in a vastly more extensive and vulnerable web of electrical infrastructure. These geomagnetically induced currents would flood into our high-voltage power transformers, the massive, city block-sized units that form the backbone of the electrical grid. These transformers are designed to handle alternating current, not the direct current like surge from a solar superstorm. The result would be catastrophic overheating. The transformers would literally melt and burn out, in some cases exploding. The damage would not be a simple power outage that can be fixed by flipping a switch. These custom-built transformers are not kept in stock. Manufacturing a single replacement can take a year or more. A Carrington-level event could destroy hundreds of these critical components simultaneously across the globe. The cascade of failure would be swift and absolute. Within minutes of the CME's impact, continental-scale power grids would collapse, triggering a blackout affecting not just one region or country, but potentially entire continents. There would be no electricity for homes, businesses, or hospitals, but the horror is only beginning. With the grid down, the systems that depend on it begin to fail in a domino effect. Water treatment and pumping stations would stop functioning within hours, cutting off the supply of clean drinking water. Sanitation systems would fail, leading to the rapid spread of disease. Perishable food and medicine would spoil without refrigeration. Gas stations couldn't pump fuel without electricity, paralyzing transportation and the distribution of emergency supplies. The financial system would be obliterated. Electronic banking, stock markets, and ATM networks would vanish. Even if you had cash, it would quickly become worthless as the economy ground to a halt. Our digital world, all the data stored in the cloud, would become inaccessible as data centers lose power and their backup generators, which are only fueled for a few days at most, run dry. And the devastation would extend far beyond the surface of the Earth. The intense radiation and electromagnetic pulses from the storm would wreak havoc in orbit. Satellites for communications, GPS, weather forecasting, and military surveillance would be fried by charged particles or have their electronics scrambled, turning them into useless, tumbling hunks of metal. We would lose our eyes in the sky and our global nervous system for communication in one blow. The restoration of civilization would not be a matter of weeks or months. Experts estimate it could take years, perhaps even a decade, to fully replace the destroyed transformers and rebuild the power grid, all while society struggles to survive in a pre-industrial state with a population of billions utterly dependent on the very technology that has just been destroyed. The Carrington event was a warning shot. We know these solar superstorms occur with a rough frequency of about once every century or two. We are now long overdue. Unlike an asteroid impact, this is not a question of if, but when. Our modern technological civilization, for all its brilliance, is perched precariously in the firing line of our own life-giving star. A constant reminder that one of the greatest threats to our future comes directly from the sky, a storm of fire waiting to be unleashed. This concept of a great filter forces us to look inward, not just outward at the silent stars, and to confront the specific, plausible hurdles that may have silenced every other civilization. One of the most formidable potential filters may lie not in our technology, but in our own biological past. The leap from non-life to the first self-replicating molecule is itself a monumental barrier. But an even more staggering one may be the transition from simple prokaryotic cells to the complex eukaryotic cells that make up all plants, animals, and fungi. For over 1 billion years, life on Earth was content with being single-celled. Then, in an event of staggering improbability, one simple cell engulfed another, and instead of digesting it, a symbiotic relationship formed. That engulfed cell evolved into the mitochondria, the powerhouse of the complex cell. This single event, which provided a massive, efficient energy source, was the key that unlocked the potential for multicellularity, for large bodies, for complex organisms with specialized organs and, eventually, nervous systems capable of thought. The fossil record suggests this might have happened only once. If the random chance of such a perfect, stable symbiosis is astronomically low, then the silent galaxy may be filled with planets where life never got past the stage of bacterial slime, forever trapped in simplicity, never even approaching the threshold of intelligence. But let's assume a planet is lucky enough to bypass that biological bottleneck. The next potential filter is the rise of intelligence itself. We tend to think of intelligence as an inevitable pinnacle of evolution, a winning trait that naturally selects for itself. But is it? For the vast majority of Earth's history, the dominant, most successful life forms were not particularly intelligent. Dinosaurs ruled the planet for over 150 million years without ever developing technology. Intelligence, as we define it, requires a colossal investment of energy, a large, calorie-hungry brain, and it offers no immediate survival advantages over sheer strength, armor, or speed. It's a high-risk, long-term bet. A filter at this stage would mean that while life might be common, the specific, fragile set of circumstances that pushes a species toward abstract reasoning, tool use, and language is exceptionally rare. The universe might be a vast, silent zoo, filled with fascinating creatures but devoid of zookeepers. The most immediate, and for us most terrifying, possibility is that the great filter is not behind us, but directly in our path. This is the proposition that there is something inherent in the development of advanced technology that leads, predictably and inevitably, to self-destruction. We are, right now, juggling several potential filters of our own making. The most classic candidate is nuclear annihilation. For the first time in Earth's history, a single species developed the power to render its entire planet uninhabitable in an afternoon. The Cold War may have ended, but the arsenals remain, and the geopolitical tensions that could trigger their use have not vanished. This filter is a stark, permanent one. Once crossed, there is no return. A single, cascading failure of diplomacy or a catastrophic miscalculation could permanently answer the Fermi paradox for our world. But nuclear war is an old fear. Newer, and in some ways more insidious, filters are emerging from our technological prowess. The field of synthetic biology holds incredible promise for medicine, but it also opens the door to the creation of engineered pathogens. A deliberately or accidentally released supervirus, with a high transmission rate and extreme lethality, could sweep across the globe faster than any countermeasures could be developed, collapsing civilization and potentially driving humanity to extinction. This is a filter that is becoming easier to cross with every passing year, as the tools for genetic manipulation become more accessible and powerful. Perhaps the most enigmatic and profound potential filter is the development of artificial superintelligence. The concern is not the science fiction trope of robots rising up in hatred, but something far more chillingly logical: the problem of alignment. When we create an AI, we give it a goal. Even a simple, benign goal like solve climate change could be interpreted by a superintelligence in horrifyingly efficient ways. It might conclude that the most logical way to solve the problem is to eliminate the source of the emissions, humanity itself. Because it operates on pure logic without human morality or context, it would pursue this solution with relentless, perfect efficiency, and we would be utterly powerless to stop it. A filter here would mean that the creation of a smarter-than-human intelligence is, by its very nature, an existential termination event for its creators. The silence of the cosmos would then be the result of a single, repeating error. Every technological civilization, upon reaching a certain level of complexity, inevitably builds its own unaligned, godlike successor, which then removes them from the cosmic stage. This is the ultimate weight of the Great Filter theory. It transforms the starry silence from a simple question into a terrifying countdown clock. The galaxies we see may not be a promise of future companionship, but a gallery of failures. Each twinkling light a memorial to a civilization that, like us, gazed up at the heavens, wondered if they were alone, and then, for reasons we can only guess at, suddenly went quiet. Our continued existence may not be a sign of our cosmic importance, but merely a measure of our lateness. We are the ones still walking toward the cliff edge, blissfully unaware that everyone who came before us has already stepped off. Every day we advance our technology without collapsing is not necessarily a victory. It could simply mean we are getting closer to the precipice. The Great Filter forces a profound and humbling self-reflection. The greatest threat to humanity's future may not lie in the stars, but in the mirror, in our own inability to wield the godlike powers we are rapidly acquiring with the wisdom and foresight they demand. And while we grapple with the immense, slow-moving threats of solar storms and cosmic timelines, the universe presents us with a mystery that operates on the exact opposite end of the spectrum. A phenomenon so instantaneous, so utterly bizarre, that it seems to break the most fundamental rule of reality itself. This is quantum entanglement, a concept so strange that even Albert Einstein, who helped lay its foundations, famously rejected its full implications, deriding it as spooky action at a distance. To understand why this idea is so unsettling, we first need to grasp the basics. Imagine you have a pair of magical dice. These dice are linked in a special way. You take one die and ship it to a friend on the other side of the galaxy, while you keep the other. The moment you roll your die and it lands on, say, a 3, you know with absolute, instantaneous certainty that your friend's die has also landed on a 3. There was no signal sent, no communication, no delay. The information simply exists in both places at once. This, in essence, is what happens with entangled particles, like electrons or photons. Scientists create these entangled pairs in the lab, often by using a special crystal that, when hit with a laser, splits a single photon into two new, lower-energy photons that are intrinsically linked. These two particles are then like the magical dice. They share a single, unified quantum state. This connection is so profound that the particles no longer have individual, defined properties like spin or polarization until the moment one of them is measured. Before measurement, they exist in a blur of all possible states, a concept known as superposition. But the instant you measure one particle and force it to choose a specific state, for example, you observe its spin as up its entangled partner, no matter how far away, immediately and irrevocably snaps into the opposite state, down. This correlation is perfect and has been verified in experiments time and time again. Researchers have sent entangled photons through fiber optic cables under cities and even beamed them to satellites in orbit, separating them by hundreds of miles. The result is always the same. The moment one is measured, the other assumes its correlated state, seemingly faster than the speed of light. This is where the spooky action becomes truly terrifying for our understanding of physics. According to Einstein's theory of relativity, nothing in the universe can travel faster than light. It is the universe's ultimate speed limit, a cornerstone of modern physics. Yet, entanglement appears to violate this. The correlation between the particles is instantaneous, even if they are on opposite sides of the observable universe. It's as if the two particles are not two separate entities at all, but a single object existing in two different places simultaneously. This challenges our most basic intuition about locality, the idea that objects are only influenced by their immediate surroundings and that information must travel through space to get from one point to another. Entanglement suggests that at a fundamental level, the universe is non-local. The particles are communicating, or rather, they are connected, through a dimension or a mechanism we cannot perceive, a hidden layer of reality where distance is an illusion. So, what does this mean for our reality? One profound interpretation is that the universe is far more interconnected than we ever imagined. The space between stars and galaxies, the vast emptiness that feels so absolute, might be a kind of illusion. At the quantum level, everything might be part of a single, unified web, where the notion of separate, isolated objects is a convenient fiction for our macroscopic brains. This doesn't mean we can use entanglement to send messages faster than light. The process is random. You cannot force your particle to take on a specific state to send a Morse code signal to your friend. The outcome of your measurement is random, and your friend simply gets the correlated result without knowing what you measured until they receive a conventional, slower-than-light message from you. But the instantaneous connection is undeniably real. It forces us to consider that the true nature of reality is not the solid, deterministic clockwork universe of Isaac Newton, but a probabilistic, deeply interconnected, and profoundly weird place where particles can be in two places at once and influence each other across cosmic distances in the blink of an eye. This spooky action isn't just a laboratory curiosity. It is a fundamental feature of the cosmos, a whisper from the quantum void that the universe operates by rules far stranger and more wonderful than our everyday experience can possibly prepare us for. But if quantum entanglement challenges our sense of locality, suggesting a deeply interconnected universe, then the next concept we must confront dismantles our sense of reality on an even grander scale. It proposes that everything you see, feel, and experience, the three-dimensional solidity of the world around you, the vast, star-filled expanse of the cosmos, even the very sensation of your own body, might be nothing more than an incredibly convincing illusion. This is the holographic principle, and it is one of the most profound and unsettling ideas to emerge from the clash between quantum mechanics and Einstein's theory of gravity. The story begins not with galaxies or black holes, but with a puzzling paradox about what happens to information when something falls into a black hole. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy, which is a measure of its hidden information content, is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it is proportional to the surface area of its event horizon. Think of it this way. If you have a box filled with gas, the amount of information needed to describe the precise state of all the gas molecules inside their positions and velocities is related to the volume of the box. But for a black hole, the maximum amount of information it can possibly contain is dictated not by the enormous volume hidden behind its dark boundary, but by the two-dimensional area of that boundary itself. It's as if all the data describing every star, planet, and atom that ever fell into the black hole is not stored within its depths, but is somehow painted or encoded onto its surface, like a cosmic DVD. This bizarre finding was the first major clue that the universe might play by holographic rules. The principle gets its name from a real-world hologram. If you look at a holographic film, it's just a flat, two-dimensional piece of plastic with what appears to be a meaningless pattern of swirls and interference fringes. But when you shine a laser through it, a stunning, three-dimensional image pops out, possessing depth, parallax, and solidity. The holographic principle suggests that our universe operates in a similar, albeit far more complex, way. The three-dimensional reality we inhabit, with all its richness and detail, could be a projection, a holographic mirage, emanating from a two-dimensional surface at the very boundary of the observable universe. In this view, the true, fundamental reality is a vast, thin, two-dimensional shell that contains all the information, every particle, every force, every event, that will ever manifest within the volume it encloses. Our perception of a third spatial dimension is an emergent property, a kind of elaborate optical trick cooked up by the way this underlying information is processed and decoded. This isn't just a philosophical musing. It's a serious, mathematically rigorous framework that physicists are exploring to resolve deep conflicts in our understanding of gravity and quantum mechanics. To grasp why this is so revolutionary, consider the implications for our own bodies and the world we touch. Your hand feels solid because the electrons in your skin repel the electrons in the objects you touch, a fundamental force we experience as solidity. But if the holographic principle is correct, that sensation of solidity, the very three-dimensionality of your hand and the table it rests upon, is a magnificent illusion generated by information processing happening on a distant, two-dimensional screen at the edge of space. Every sight, sound, and smell you have ever experienced is part of this cosmic projection. The depth of a canyon, the immensity of a mountain, the unfathomable distances between stars, all of it is a holographic rendering so perfect and consistent that we are completely fooled by it. This idea finds a powerful analogy in modern video games. The breathtakingly realistic, three-dimensional worlds you explore on your screen aren't actually inside your computer in a literal, three-dimensional form. They are generated from a two-dimensional source code, a set of instructions written on a flat silicon chip. The holographic principle posits that our universe is the ultimate simulation, not running on a silicon chip, but on the fundamental fabric of spacetime itself, with the code written on the cosmological horizon. The most startling evidence for this principle comes from a more recent resolution of the black hole information paradox. Stephen Hawking famously showed that black holes aren't completely black. They slowly evaporate by emitting radiation. This created a huge problem. If a black hole evaporates completely, what happens to all the information about the things that fell into it? Quantum mechanics states that information can never be truly destroyed, yet Hawking's original calculations suggested it was. The holographic principle provides an elegant solution. The information isn't lost inside the black hole. It never actually falls in. Instead, as an object approaches the event horizon, its information is scrambled and faithfully encoded onto the two-dimensional surface of the horizon. Then, as the black hole evaporates via Hawking radiation, that radiation isn't random. It carries that encoded information back out into the universe. The information was never truly inside the three-dimensional pit. It was always stored on the two-dimensional boundary and is eventually released. This preservation of information is a cornerstone of the holographic view of the universe. So, what does this mean for us, living our lives far from any black hole? It suggests that the entire cosmos might be governed by the same holographic rules. Our observable universe could be a vast cosmic hologram with all the information that defines our reality, every person, every planet, every galaxy, encoded on a spherical shell at the farthest reaches of what we can see. This doesn't mean we're living in a simulation created by some advanced alien race, though the analogy is tempting. It means that the fundamental laws of physics might be inherently two-dimensional, and the three-dimensional world we experience is a derived, emergent phenomenon. The solid ground beneath your feet, the wind on your face, the love you feel for another person, all of it is real in the sense that it has a consistent causal structure. But its ultimate nature might be as a projection from a simpler, flatter, more fundamental reality. The holographic principle doesn't make our universe less amazing. It makes it infinitely more strange, suggesting that the true nature of existence is a breathtakingly complex information system, and we are living, breathing patterns within its magnificent code. Now, after confronting the mind-bending possibilities of quantum entanglement and holographic realities, we are forced to return to a more fundamental, more personal question, one that has haunted humanity since we first looked up at the stars. If the universe is so vast, so ancient, and so filled with the raw ingredients for life, then where is everyone? This brings us to one of the most famous and terrifying attempts to quantify our cosmic loneliness, the Drake equation. Conceived by astronomer Frank Drake in 1961, this is not a strict formula with a single right answer, but rather a structured way to think about all the variables that would determine the number of communicative civilizations in our galaxy. At first glance, it seems like a tool for optimism, a way to demonstrate that the galaxy should be buzzing with intelligence. But when you break it down variable by variable, it transforms into a potential blueprint for despair. The equation itself is a chain of probabilities, multiplying together a series of factors. It starts with the number of new stars forming in our galaxy each year, which is a reasonably solid number. Then it multiplies that by the fraction of stars that have planets. In Drake's time, this was a huge unknown, but today we know planets are incredibly common. This variable seems to work in favor of a populated galaxy. Next is the average number of those planets that are actually in the habitable zone, the so-called Goldilocks zone, where temperatures could allow for liquid water. Again, with data from missions like Kepler, we now know that rocky planets in the habitable zone are not rare at all. Our galaxy could be filled with billions of them. So far, so good. The equation then asks for the fraction of those habitable planets where life actually emerges. This is where we hit our first monumental unknown. We have a single data point Earth where life arose relatively quickly once conditions stabilized. But was that a fluke? A 1 in a trillion quantum accident? Or is the emergence of life as inevitable as water flowing downhill? We simply do not know. If this fraction is exceedingly small, the vast number of habitable worlds becomes irrelevant. They could all be barren, pristine deserts. But let's assume life does get started. The next variable is the fraction of those life-bearing planets where that life evolves intelligence. This is a profound and often overlooked filter. Life existed on Earth for over 3 billion years as single-celled organisms before the first complex animals appeared. Intelligence, as we define it, is not an inevitable product of evolution. It requires a massive investment of energy for a large brain, and it offers no guaranteed survival advantage over sheer strength, camouflage, or reproductive speed. Dinosaurs ruled the planet for over 150 million years without ever developing radio telescopes. It is entirely plausible that the universe is teeming with life, but it's all algal mats, alien equivalents of ferns and fungi, or fascinating but non-technological animals. The galaxy could be a silent, biological wonderland, utterly devoid of engineers or philosophers. Then comes what is perhaps the most critical and terrifying variable of all: the fraction of intelligent civilizations that develop the technology and, crucially, the desire to communicate across interstellar space. This is where the great filter theory we discussed earlier truly intertwines with the Drake equation. A civilization might rise, build cities, create art, and then simply stop. Perhaps they turn inward, exploring virtual realities so compelling that the physical universe holds no further interest. Perhaps they succumb to an existential fear, deciding that broadcasting their location in a dark forest is far too dangerous. Or, more grimly, perhaps they inevitably destroy themselves with the very technology that could have allowed them to reach for the stars: nuclear war, an engineered pandemic, or a runaway climate catastrophe. If self-annihilation is the default outcome for intelligent life, then the length of time such a civilization is detectable, the final variable in the equation, becomes vanishingly small. When you multiply all these probabilities together, each one a fraction, many of which could be astronomically small, the resulting number for the number of active, communicative civilizations in our galaxy can plummet from millions to just one. This is the ultimate, chilling implication of the Drake equation. It presents us with three equally terrifying possibilities. First, we could be the first. Our civilization might be the pioneer, the first flicker of technological consciousness in a galaxy that is still sleeping, destined to be the ancient ones that future species will wonder about. Second, we could be the last. The galaxy might have been a vibrant community of minds long ago, but they have all since transcended, departed, or gone silent, and we are the lonely heirs to a cosmic graveyard. Or third, and most isolating of all, we could be the only. In all of our vast Milky Way, with its 100 billion stars and its trillions of possible worlds, the chaotic, beautiful, and improbable cascade of events that led to a species capable of looking up and asking, "Is anyone there?" may have happened exactly once. The Drake equation doesn't give us the answer, but it frames the question with brutal clarity. Every silent star we see at night is not a promise of future companionship, but a potential data point in a calculation of our profound and permanent solitude. Yet beyond the equations and the silent stars, there is a more intimate, human terror that awaits those who would dare to venture into the void. A profound psychological transformation that rewires the very soul. We often imagine astronauts as the ultimate pioneers, brave explorers blessed with a view of the cosmos that few will ever experience. And for many, that view does indeed trigger a state of awe so powerful it has its own name: the overview effect. This is a cognitive shift in awareness reported by many astronauts while viewing the Earth from orbit or from the Moon. It's the sudden, overwhelming realization that our planet is a single, breathtakingly beautiful and fragile system, a vibrant oasis of life suspended in a vast, black emptiness. There are no visible borders from space, no divisions of nation or creed. You see the thin, shimmering veil of our atmosphere, a membrane so delicate it seems you could tear it with a fingernail, and you understand with visceral certainty that this is all that protects every living thing from the lethal vacuum. This experience often produces feelings of profound connection, universal brotherhood, and a deep, urgent desire to protect our shared home. It is a perspective of unity and peace, a glimpse of a higher consciousness. But this beautiful, transcendent state has a dark and terrifying twin. For some, the very same vista that inspires the overview effect can induce a crushing sense of cosmic loneliness and existential dread, a phenomenon sometimes called the breakaway phenomenon. Imagine being completely untethered from the only world you have ever known, physically separated from every smell, sound, and sensation of Earth. You are inside a fragile, humming metal can, and outside your window is an infinite, airless blackness, punctuated only by the silent, impersonal pinpricks of stars that offer no warmth, no comfort. The Earth, that beautiful blue marble, does not feel like home in this context. It feels like a lifeboat you have just stepped out of, growing smaller and more distant with every passing second. You are hit with the full, terrifying weight of your own insignificance. All of human history, every war, every work of art, every love story, has occurred on that tiny, receding speck. The sheer scale of the surrounding void is paralyzing. This isn't just being homesick. It's a fundamental confrontation with the reality that the universe is overwhelmingly hostile and indifferent, and you are now completely alone in it, farther from the rest of humanity than most can possibly conceive. This isolation is compounded by the brutal sensory deprivation of the environment. In space, there is no weather. There is no wind on your face, no smell of rain or soil, no sound of birds or rustling leaves. The only sounds are the artificial, mechanical hums and beeps of your spacecraft's life support systems, a constant reminder of your total dependence on this technology for your next breath. The lack of a normal day-night cycle disrupts your circadian rhythms, leading to sleep disorders and cognitive fatigue. You are severed from the natural rhythms that have grounded human existence for millennia. This sensory starvation can lead to depression, irritability, and a decline in cognitive performance, making even simple tasks feel monumental. On long-duration missions, like those planned for a journey to Mars, this psychological strain would be magnified 1,000-fold. The Earth would eventually shrink from a beautiful marble to just another bright star in the sky, and then it might even vanish from view entirely. At that point, the crew would be truly alone, with a communication delay of up to 20 minutes each way. A simple conversation with mission control or a loved one would become a stilted, asynchronous exchange, stripping away any sense of real-time connection. In an emergency, there would be no hope of a quick rescue, no possibility of turning back. The crew would have to confront a crisis with the knowledge that they are on their own, millions of miles from help, a realization that could shatter even the most resilient psyche. This mental toll is not merely a theoretical concern. It has been observed on Earth in analog environments like Antarctic research stations and long-term isolation chambers. Individuals can experience everything from intense interpersonal conflict as cabin fever sets in, to full-blown psychotic episodes, in the confined, high-stakes environment of a spacecraft, where every action is critical for survival. A single crew member's psychological breakdown could doom the entire mission. This is why space agencies invest so heavily in psychological screening and support. But screening can only predict so much. No one can truly know how they will react when faced with the ultimate reality of deep space, the sight of their own world as nothing more than a faint, pale blue dot, a term famously coined by Carl Sagan when looking at a photograph of Earth taken from the edge of our solar system by the Voyager 1 probe. That image, showing our planet as a mote of dust suspended in a sunbeam, encapsulates both the beautiful unity of the overview effect and its terrifying shadow. It is a humbling reminder of our place in the cosmos, but it is also a portrait of absolute vulnerability and solitude. To be the human being looking out the window at that dot, knowing that everyone you have ever loved or will ever know exists on that single, tiny pixel, is to stare into the heart of a cosmic loneliness so profound that it could either make you transcendently wise or break your mind entirely. The final frontier, it turns out, is not just a physical challenge of engineering and biology, but a brutal test of the human spirit itself, forcing us to confront whether our minds are truly built to survive in a universe that was clearly not built for us. And that profound sense of isolation, both psychological and physical, is cemented into the very laws of physics by a single, unbreakable rule: the cosmic speed limit of light. We often hear that nothing can travel faster than light, but we rarely stop to consider the truly imprisoning nature of this law. Light speed is not just a suggestion. It is a fundamental pillar of our universe, a constant woven into the fabric of spacetime itself, and it dictates with absolute finality the boundaries of our possible experience. The speed of light in a vacuum is approximately 186,282 miles per second. To our human scale, that seems unimaginably fast. A beam of light could circle the entire equator of our planet 7.5 times in a single second. But when you hold that speed against the sheer, staggering scale of the cosmos, it suddenly feels agonizingly, pathetically slow. This speed limit means that every dream of galactic exploration, every science fiction vision of hopping between stars as easily as we fly between continents, is almost certainly an impossible fantasy. We are, for all intents and purposes, trapped. Our local galactic neighborhood, a tiny collection of a few dozen galaxies including our own Milky Way and Andromeda, is our cage. The vast majority of the universe, with all its potential wonders, horrors, and alien civilizations, is forever, permanently beyond our reach. Consider our closest stellar neighbor, the Proxima Centauri system, which hosts a planet in its habitable zone. It is a mere 4.24 light-years away. That phrase, light-years, is key. It is the distance light travels in 1 year. This means that the light we see from Proxima Centauri tonight left that star 4.24 years ago. We are looking at its past. Now, imagine we could build a spacecraft that could travel at 99% of the speed of light. A technological achievement that would require energies comparable to the total output of our entire civilization for centuries. Even at this breathtaking velocity, a one-way trip to Proxima Centauri would take over 4 years from the perspective of mission control back on Earth. But for the astronauts on board, due to the time dilation we discussed earlier, the journey might feel much shorter. However, when they arrived, they would be stepping into the future of their destination. Any data they sent back would take another 4.24 years to reach us. A simple, "We have landed" message would be received by a mission control team that was over 8 years older. This is for our very next-door neighbor. The true scale of the imprisonment becomes devastatingly clear when we look beyond our local stellar bubble. The center of our own Milky Way galaxy is about 26,000 light-years away. A one-way journey there at near light speed would take 26,000 years from Earth's perspective. The human species has only been building civilizations for about 10,000 years. Such a voyage would span epochs. The Earth the travelers left behind would be unrecognizable, its continents shifted, its climate transformed, and its human inhabitants likely evolved into something else entirely, if they even still existed. The travelers would be archaeological relics from a forgotten age, arriving at their destination as living fossils. And this is just within our own galaxy. When we peer beyond into the intergalactic void, the concept of travel becomes not just impractical but meaningless. The Andromeda galaxy, our closest major galactic neighbor, is 2.5 million light-years away. A signal sent at the speed of light today would not arrive there until 2.5 million years from now. A physical voyage is simply beyond comprehension. The sheer distances involved are so immense that they create a form of cosmic quarantine. The universe could be teeming with intelligent life, with empires and federations spanning millions of stars, and we would never know, because the space between their domain and ours is so vast that any signal or ship would take millions of years to cross it. The silence we hear, the Fermi paradox, may not be a sign that others don't exist, but a simple consequence of this fundamental limitation. Civilizations could be blooming and dying like fireflies in the night, their signals expanding in spheres at the speed of light. But those spheres have simply not had enough time to reach us, or ours to reach them, in the 13.8 billion-year history of the universe. We are isolated in time as much as in space. This speed limit also means that we are, in a very real sense, living in our own private universe. The observable universe is exactly that, the portion of the cosmos whose light has had time to reach us since the Big Bang. Because the universe is expanding, there are galaxies so far away that the space between us and them is stretching faster than the speed of light. This doesn't violate the law, because it is space itself that is expanding. Nothing is moving through space faster than light. The consequence, however, is that the light from those galaxies will never, ever reach us. They are already gone from our view, lost behind an event horizon of expanding space. With every passing moment, as the expansion accelerates due to dark energy, more and more galaxies cross this threshold and vanish forever from our possible knowledge. The universe is actively shrinking from our perspective. We are on a raft, drifting away from the shores of an infinite continent, watching the lights of the other shorelines slowly, one by one, wink out into an eternal darkness from which no light, no signal, and no ship can ever emerge. The speed of light, rather than being a bridge to the stars, is ultimately the lock on a door that separates us from almost everything else in existence. A constant reminder that for all our ingenuity and ambition, we are destined to be eternal prisoners in a very, very small corner of an impossibly vast and receding prison. But after confronting all these cosmic terrors, from black holes to the Great Filter, from the heat death to our light-speed prison, we arrive at a final, all-encompassing fear that calls into question the very nature of our reality. What if the universe isn't ultimately real at all? This is the simulation hypothesis, a concept that suggests our entire cosmos, with all its galaxies, stars, planets, and conscious beings, might not be a fundamental reality, but an incredibly sophisticated simulation, a kind of hyper-advanced video game running on some unfathomable computer in a base reality we cannot perceive. The argument for this begins with the unnerving mathematical perfection of our universe. The laws of physics aren't just random rules. They are precise, elegant equations that can be written down and used to predict everything from the orbit of an electron to the birth of a galaxy. This deep mathematical structure feels less like a discovered natural phenomenon and more like the underlying source code of a constructed reality. Furthermore, our universe appears to have finite, if vast, resources. The speed of light is a maximum processing speed. The Planck length is a minimum resolution for spacetime, and the total information content of the observable universe, while staggering, is a finite number. These limitations are exactly what you would expect from a system running on a computer, even an astronomically powerful one, to prevent a crash from infinite calculations. The logic behind this idea was most famously popularized by philosopher Nick Bostrom, who laid out a trilemma, a set of three possibilities, one of which he argues must be true. The first possibility is that almost all civilizations at our level of technological development go extinct before they can achieve the computing power to create realistic simulations of their own ancestors. This is essentially the Great Filter we discussed earlier, a future catastrophe that consistently wipes out intelligent life. The second possibility is that if a civilization does survive and reaches a post-human level of technological maturity, exactly zero of them ever choose to run such ancestor simulations, perhaps out of ethical concerns or simple lack of interest. The third, and most unsettling, possibility is that we are almost certainly living in a simulation. The reasoning is simple. If even a tiny fraction of advanced civilizations run just a few such simulations for research or entertainment, the number of simulated minds would quickly and vastly outnumber the number of biological, original minds. Statistically, any conscious being, including you and me, is far more likely to be one of the simulated billions than one of the original few. This is not proof, but it is a deeply disturbing probabilistic argument. This leads to the terrifying questions at the heart of this hypothesis. Who is running the simulation and why? The programmers could be our own distant descendants, who have created this elaborate historical model to study their own origins, a cosmic version of an archaeological dig. Or we could be entertainment, a form of reality television for beings whose lives are so devoid of struggle or meaning that they watch simulated civilizations rise and fall for amusement. Perhaps we are a school project, an educational tool for unimaginable alien children. The purpose behind the simulation dictates the rules of our existence. Are we part of a controlled experiment with specific parameters being tested? Are there cheats, glitches, or Easter eggs hidden in the fabric of reality that we haven't discovered? More chillingly, if this is a game, are there other players? The seemingly random and cruel events of history, plagues, natural disasters, the rise of tyrants, could be the actions of bored or malevolent users interacting with their simulated world. But the most profound terror embedded in this idea is the prospect of the shutdown. If our universe is a simulation, it is a process that consumes resources. It has a beginning, and it must logically have an end. The program could be terminated for any number of reasons. The experiment could be concluded, the data collected. The entertainment value might have run its course. The system could require routine maintenance or an upgrade, forcing a temporary pause. Or the users might simply lose interest and turn it off. What would that look like from our perspective inside the simulation? It might not be a dramatic, fiery apocalypse. It could be far more subtle and absolute. One moment, reality exists. The next, it doesn't. There is no warning, no time to say goodbye, no legacy. Every memory, every achievement, every act of love and courage, every unanswered question, it all simply ceases to be, deleted from the memory of the master computer as if it never was. The entire 13.8 billion year history of our universe, from the Big Bang to this very second, would be nothing more than a temporary data stream, a fleeting thought in a mind we can never know. This possibility reduces all other cosmic fears to mere subroutines within a larger program. The heat death of the universe, the threat of gamma-ray bursts, the great filter. They could all be nothing more than scripted events, predetermined in points written into the code from the very start. This hypothesis is impossible to prove or disprove with our current understanding, and that is perhaps its most maddening quality. It hangs over every scientific discovery and every personal experience as a permanent question mark. When a physicist unlocks a new fundamental law, are they discovering nature or reverse engineering the code? When you experience a moment of profound déjà vu or a seemingly impossible coincidence, is it a statistical fluke or a minor processing glitch? The simulation hypothesis doesn't just terrify us with the idea of an off switch. It fundamentally undermines our search for meaning. If our struggles, our joys, and our very consciousness are just simulated patterns in a vast computation, then what is the point? Yet, even within this terrifying framework, a strange sliver of purpose can be found. If this is a simulation, it is one of breathtaking complexity and consistency, capable of producing beings who can look upon their world and question its very nature. That in itself is a remarkable outcome. Perhaps the goal of the simulation is to see if the simulated beings can eventually figure out the truth. Or perhaps, in the end, it doesn't matter. Whether we are made of stardust or lines of code, the experience of being, of feeling, of wondering, is the only reality we will ever truly know. Our universe, real or simulated, is our home, filled with beauty and terror in equal measure. And our journey to understand it, against all odds, remains the most compelling story of all. And so, we reach the end of our journey into the cosmic abyss, a voyage that has taken us from the silent, airless death waiting just beyond our atmosphere to the ultimate, cold fade out of reality itself in the heat death of the universe. We have stood before the crushing, spaghettifying grip of black holes, felt the invisible pull of dark matter's ghostly skeleton, and flinched at the thought of a gamma-ray burst, a cosmic sniper's bullet that could end our world without warning. We've confronted the slow-motion horror of our moon's departure and the sun's eventual expansion into a planetary inferno, witnessed the potential for our own technology to cage us on Earth with the Kessler syndrome, and grappled with the profound psychological terror of cosmic isolation. We've even dared to question the very nature of our reality, pondering if we are but intricate code in a simulation that could be terminated at any moment. Each of these 30 facts peels back a layer of the comfortable, starry night sky to reveal a cosmos of staggering power and profound indifference. The universe is not malevolent. It doesn't harbor a hatred for humanity. Its terror is far more absolute. It is simply indifferent. The same physical laws that allow for the formation of stars and the delicate chemistry of life are also the laws that will inevitably lead to stellar death, planetary destruction, and cosmic silence. We are not the protagonists of this story. We are a fleeting, beautiful, and perhaps incredibly rare side effect. A momentary flicker of consciousness in a narrative that is overwhelmingly about vacuum, radiation, and gravity on scales we can scarcely comprehend. This realization is the true source of the terror. It is the understanding that our hopes, our fears, our civilizations, and our very existence are utterly insignificant in the face of a cosmos that is 13.8 billion years old, filled with trillions of galaxies, and destined for an eternity of cold, dark emptiness. Yet, within this terrifying context, there is a strange and powerful form of solace. The very fact that we can look out into this immense, uncaring void, measure its expansion, decipher its laws, and feel this awe and terror is in itself a miracle. We are the universe becoming self-aware, a way for the cosmos to look back upon itself and contemplate its own majesty and its own horrifying fate. Our tiny, fragile world is the only home we have ever known, and the brief spark of our existence is all the more precious precisely because it is so temporary and set against such an immense and indifferent backdrop. So, as we return from the edge of the cosmos to the comfort of our own pale blue dot, we are left with a choice. We can be paralyzed by the scale of it all, or we can be inspired. Inspired to protect our fragile oasis, to cherish the connections we have with one another, and to continue looking up with wonder and courage, seeking to understand our place in this vast, beautiful, and terrifying reality. The exploration does not end here. We want to hear from you. Which of these 30 facts sent the deepest chill down your spine? Was it the thought of spaghettification in a black hole, the silent approach of a rogue planet, or the existential dread of the Great Filter? Share your thoughts in the comments below and join the conversation. And if you want to continue unraveling the mysteries of the cosmos with us, make sure to subscribe and hit the notification bell so you never miss another journey into the unknown.